So, welcome everyone. This is Nicola Marzari from EPFL, and I have the great pleasure of introducing the fourth event in our Cecam Marvel series on classics in molecular and materials modeling. Today with Professor Tony Ladd from the University of Florida and Professor Dan Frankel from Cambridge University. And this series is run together with Cecam, the European Center of Atomic and Molecular Computation, that actually we are very happy and honored to have here hosted on campus at EPFL, led by Professor Ignacio Pagonaraba, that is here, the director and the deputy director, Dr. Sara Bonella, and they will be mostly running the event today. But before going into today's activity, let me actually mention two more events that are forthcoming. The first one organized by Cecam, the very insightful mixed generation session. This time it will be on activated events, and we'll have as the senior speaker Professor Alessandro Laio from CISA, and the two junior speaker and a poster session on Gather Town. That's also very much a community event. And that will be on June 3rd at 3 p.m. And then on June 15 at 2 p.m. We have one of our Marvel distinguished lectures. It will be Professor Dario Gil, that is the director of IBM Research worldwide on accelerated materials discovery and quantum computing. But to go back to today's event, here I have the program, and I think in particular for the science that will be presented, there is a very sweet and dear connection to Cecam activities. So it's, I think, very appropriate to give the word to Professor Pagonabarraga to introduce actually today's event. Ignacio, please.
Yeah, thank you, Nicola. And yeah, thank you and welcome everybody to this new installment of this series. This is a series of special lecture series where we take a different look at fundamental developments of simulations and modeling. And basically, we identify milestone conceptual steps and tools and methods and invite their originators with the goal that they can explain to us what they did it and how and what was behind this advance. And also, this is in the first part, but then also in a second moment to find a more informal way to have an interview so that we have the possibility that the speakers can recall for us the period, the circumstances that accompanied these developments, and also on a more personal level about how this came about and try to get more insight into the nature of science discoveries that normally are not so obvious or are more hidden in the standard ways in which we tend to convey and to transmit science through scientific events. In this event in particular, we will focus on an algorithm to compute the free energy of solids. And this actually is quite keen or close to Cecam because it originated actually from a Cecam workshop in 1983 on dynamics of molecular liquids under external constraints. That was an event that lasted for almost a month. So it's different from the type of workshops that we organize in more recent years. So it will be interesting to understand the role that such an event played. I think especially now that we are suffering from the pandemics, it will be refreshing to understand the importance for the development of science that we meet together and what are the conditions that can be or can trigger or catalyze such an advance and interaction. So I'm really very much looking forward to hear from our two speakers. And as Nicola mentioned, so we have Tony Ladd. Tony started his career in Cambridge in UK, but has developed most of it in the US, the Livermore lab, and now in the University of Florida. And he has contributed significantly to the understanding and the development of algorithms for non-equilibrium systems at different scales, with always a very clear focus in trying to understand and unravel the physical phenomena that lies behind very complex situations or systems where we don't have analytic theories. And he has explored a variety of algorithms at different time and length scales. And the other speaker is Dan Frankel, who's now a professor in Cambridge and who also spent a substantial amount of his career in Amels, in the Institute Amels in the Netherlands. And again, he has quite an impressive record of contributions and research in molecular simulations in soft and biological materials. And he has contributed with, and again, with, I think both the speakers share this passion and interest in identifying the essence of the very complex phenomena and try to unravel it by ingenious algorithms. And as Dan phrases in his webpage, he develops novel algorithms when he needs them. And I think that's basically what we are also going to be exposed today, to a novel algorithm. We will try to understand why this was needed. And I hope this is for all of us a very insightful and engaging event. Now, this event is organized in the two parts that I was referring to. So we will start by two lectures provided first by Tony Ladd about thermodynamics of hard spheres from the 80s to the 80s, and a second one by Dan, which is the follow-up of how this algorithm and the ideas underlying it evolved after 1983. And these two will be separated by a break to try to minimize the Zoom fatigue. And they have a 50 minutes time allocated, but it's clear for the two of them that this time includes both their presentation and a time for questions. So all of you will have the possibility to ask any question you consider it's important or interesting at the end of their, related to the content of their presentations. And once we finish this first part, without any additional break, we will move to this interview. The interview will be shared by the Cecam Deputy Director, Sara Bonella. And here, again, this will be more a conversation where you will also be able to contribute by asking or intervening in questions that may go beyond the more technical or scientific content associated to the first two lectures. Now, if in the next, just before we move to the lecture by Tony, just a few organizational details. Nicola, can you? Yes. So basically, the lecture, the whole event will be recorded. Actually, at the end of this event, we make the event available on the Cecam YouTube channel and in the Marble Materials Cloud in the Learn section. So you can go and watch it afterwards. You can also, as it was mentioned, this is the fourth installment of this series. So the previous, if you find that this is an interesting format, you can go and check the previous one if you want to learn about the molecular dynamics under constraints that was provided by Giovanni Cicotti and Jean-Paul Ricard, or the Carr-Parinello molecular dynamics presented by Carr and Parinello, or the last one about Berry phases in condensed matter physics that was presented by Vanderbilt and Bresta. So the material is there, you can go and see what they presented and the associated conversation. They mentioned there is a possibility for you to ask questions or comments. In order to do that, since we are quite a number of people, the way to do that is to use the Q&A feature of Zoom. So you write your question or your comment, and then the chair, so either Sarah or myself, will be in charge of then relaying them to the speakers at the end of the talk and then also during the conversation. Again, in order to facilitate and to ensure the quality of the during broadcasting, you are not able to activate the sound or video, and also there is no chat feature available for you, so that then you can really concentrate on the presentation. So without any further delay, now I stop and we move. So I will now give the floor to Tony Ladd so that he can just start with the first presentation. So Tony, please now.
Okay, thanks very much, Ignacio. Let me try to get my screen share. That should be working in full screen mode. Is that correct?
Yeah, it's correct.
Okay, all right. So good morning, everyone. Thank you for joining us. It's been sort of quite fun to retrace history, to try to remember things that happened quite some time ago now. And so I'm just really grateful to Ignacio and Sarah for the opportunity to share this story with you. So the part that I'm going to describe is sort of what happened up to and immediately after the Cecam workshop. And so I sort of broken it down into 4 pieces. First, I want to talk about the Cecam workshop itself, because for me, and I think for others that were able to participate, it was a very influential event. Then I want to try and give you some idea of why it was we landed up doing Monte Carlo in a molecular dynamics workshop, and how that isn't maybe quite as inappropriate as it might seem. And then moving more towards the main content, I want to give a little bit of history of the problem of freezing of hard spheres and how that related to our understanding of liquid state theory. And then what Dan and I did at Cecam in the immediate aftermath on the problem of free energy calculations. So molecular dynamics began in, I think, 1956, when Alder presented results from his hard sphere simulations at a meeting in Brussels, I think. And the content of that talk was focusing on relatively short calculations, demonstrating that this gas of hard spheres would actually come to equilibrium, that you could calculate the Boltzmann entropy, and that it was indeed behaving in the way that you would expect from classical statistical mechanics. And that story was what molecular dynamics meant, basically solving Newton's equations of motion prior to 1980. And it was a time full of really, I think, quite amazing accomplishments. First, the establishment of a whole new way of doing statistical mechanics. And I'll spend a little bit of time on the problem of hard sphere freezing and the discoveries by Alder and Wainwright and Jacobson and Wood, because those two, both published in 1957, were very important in establishing computer simulation as a viable method for doing theoretical work, theoretical / kind of experimental work. But bringing it to the fore and having it become accepted amongst the community of scientists. And of course, there was the perhaps most famous result from Alder and Wainwright's work, which was the discovery of the long time tails in the autocorrelation functions. There's a very nice review of Alder's contributions in an article by Battimelli and Giovanni Gicotti, which was published in 2018. So in the beginning then, molecular dynamics basically meant hard particles, where you basically just check for collisions and move the particles from collision to collision. And at that time, it was thought that that was basically an exact solution. So in other words, that you would obtain meaningful trajectories from that kind of calculation, at least to the accuracy of the computer. Of course, we now understand that that isn't entirely correct because of the underlying chaotic nature of the dynamics, but that wasn't really understood at the time. Then in 1964, Anis Rahman introduced continuous potentials into molecular dynamics simulation, focusing on velocity autocorrelation functions and self-diffusion. And then later in 67, Lou Verlet introduced a simplified kind of molecular dynamics. It means simpler algorithms, same physics, but simpler algorithms, with the introduction of a symplectic integrator, which of course is the Verlet algorithm, but it was not known at that point that it was symplectic. It was basically introduced because it was simple. And then also describing in detail how you could implement neighbor lists, which was something that was also in Alder and Wainwright's molecular dynamics calculations, but not really described. And the other thing that happened in that era that was also important to our story is that Carl Moser founded Cecam at Orsay in 1969. So then in 1980, something new happened, and that there was essentially 3 different threads, all doing essentially the same thing in the sense that they were introducing equations that violated the laws of Newtonian mechanics for very specific reasons. Hans Anderson to simulate dynamical systems at constant temperature and pressure, and Bill Hoover and colleagues doing non-equilibrium molecular dynamics, trying to look at systems that are being driven far from equilibrium, and Michele Paranello and Anis Rahman introducing molecular dynamics at constant stress in order to study solid-solid phase transitions, certain classes of solid-solid phase transitions, often called Martin-Siddick transformations. And at that point, molecular dynamics becomes more than Newtonian mechanics. And just down the bottom is the only picture I could find of myself in that era, on a beach in California with my then girlfriend, now wife. This was about a year before I went out to work for Bill Hoover as a postdoc. And this non-equilibrium molecular dynamics in particular was not uncontroversial. And I remember a number of conversations trying to convince Bernie Alder that this was something worth doing. And I don't think I ever succeeded in that. Nevertheless, over time, what was once a heresy basically became an orthodoxy. And I could sense the transition when in the mid-90s I was attending AICHE meeting, mostly for the sessions on colloidal suspensions. But in the molecular dynamics sessions, there was not a single paper where people solved Newton's equations of motion. They all had some form of perturbation to the equations of motion. So those ideas that were introduced in 1980 by Anderson and by Hoover and Paranello and Rahman really became in many ways the sort of standard way of doing molecular dynamics across a wide spectrum of calculation. So in some sense, it became the orthodoxy. So in 1980, I think, or maybe somewhere between 81 and 83, Andre Bellemans, I think, conceived the idea that it will be a good thing to have a workshop to bring these 3 groups together, because although the systems they were studying were quite diverse, the techniques were remarkably similar. So if you look at the equations of motion for the constant temperature and pressure, the constant stress, and the NEMD, they're all basically involving rescaling of the coordinates and momenta according to certain prescriptions designed to do somewhat different things. So that workshop in 1983 had 13 participants, and it went on for 3 weeks, which, as Ignacio was saying, seems like a long time now, but in fact, this was the beginning of the era of short workshops. I think in previous years, typical Cecam workshops ran a month or 2 months. And in addition to that, there were people like Giovanni and Jean-Paul that were more or less permanently in residence at Orsay. So there were 13 participants. When I went there, I didn't know anybody at the workshop except for Mike Allen, who I'd been to school with, but it was an opportunity to make some new friends and start new collaborations. So for me, this was an enormous opportunity, and it led to some very interesting work over the years with Dan. So the focus of the workshop was a little different from even the Cecam workshops I attended in later years, which tended to be a fair amount of the time was consumed with people giving talks on their work. In this workshop, there was, I don't know if there were any talks. If there were, there was only 1 or 2. Most of the workshop activity was collaborative work between self-nucleating groups, and also some round table discussions. But it was an extraordinarily productive 3 weeks, I think. And here's the list of reports that Andre compiled his report at the end of the workshop from. And you can see there's like 6 different topics. Most of them related to non-equilibrium molecular dynamics or constant temperature, constant pressure, MD. And then there's this weird one at the end, which is about free energies of solids. So despite the fact that it looks completely anomalous, it isn't entirely so. So what happened was there was a discussion of the Paranello-Raman method. And during the course of the discussion, there were some limitations that were commented on. And one was that the phases must be linked by a coordinate transformation in order to apply this idea. And that it only identifies the boundaries of mechanical stability rather than the actual thermodynamic transition. Now, you might well imagine that for a lot of the martensitic transformations, the barrier to phase change is quite low, so that there may not be large amounts of hysteresis. But nevertheless, it is something that is probably a concern. So, of course, the obvious alternative was to calculate the free energy of the phases directly, and then you could tell the thermodynamic stability of any crystal structure. And the canonical way, I suppose, if anybody was actually trying to do that at that point, would be to integrate the solid from low temperatures using the harmonic reference state for the basic free energy, for the reference free energy. However, trying to integrate from low temperature, you could pass through a phase transition, which would mean that you would not be able to use that to calculate the free energy of the higher temperature solids. And then there was also the question that we were interested in, which was, what about the free energies of hard sphere systems which don't have harmonic reference states? And in the course of the discussion, what was in my mind was that the Einstein crystal was a reference that Hoover and Salzburg were using for lattice dynamics calculations. So they would calculate the phonon frequencies, but then calculate an excess entropy relative to the Einstein crystal of independent oscillators. And that just basically means it clears out a lot of the parameters that you really don't want to include in the calculation. But that was the idea of the Einstein crystal was in my head, I think. And when the discussion was going, okay, so what do we do with the free energy of solids? It was logical to think of this as a possible reference state. So one important idea, part of that idea, is that by using the Einstein crystal as a reference, so we start with the picture on the left, with the particles interacting through intermolecular forces, and then we transition to this picture on the right, where the center of mass, which is the end of the red line, it lands up being increasingly tethered to a regular array of points, which is indicated by the red circles. And so in that way, you can transition from the solid of interest to a much simpler system where it's all just single degree of freedom harmonic oscillators. And the hope was that because there was no change in crystal structure going from the state of interest to the reference state, that it would have a reversible path, and we could just integrate along that path. So here would be a typical parameterization of the potential energy. There's the potential energy of the solid itself, and then there's the potential energy, which is the sum of the forces due to the springs binding the center of mass of the particle to the lattice site. And then by changing lambda smoothly from 0 to 1, you could go from one thing to another. So that means that then that the free energy is just available as an integral over some ensemble averages. And so interestingly, the same idea was thought of by Gilmer and Broughton, and also published in 1983, although Jeremy was a friend from graduate school, we'd had no conversations about this problem. And so this was something that happened basically simultaneously and entirely independently, as is often the case in science. Of course, we weren't the first to think about thermodynamic integration. The idea was actually introduced by Kirkwood many years earlier. And what he was interested in doing was calculating chemical potential. So the basic idea was you could calculate, whoops, why did it do that? You could calculate the chemical potential by taking the difference in free energy between an n particle system and an n-1 particle system. And if n is sufficiently large, that difference will be the chemical potential. And then he introduced a similar kind of parameterization to the one that we are using, which is you basically have a sum over all of the pair interactions, except the interaction, say, with particle n, and that's the first term in that summation. And then you have another term which involves all the interactions with particle n, and that gets multiplied by some parameter. And now then you can calculate the chemical potential if you can just integrate that average potential energy as a function of lambda from lambda 0 to 1. So what that means is that you can now calculate free energy differences from ensemble averages. So that gets over the fundamental problem that you can't calculate free energies by sampling. However, in 1935, the requirement, the actual calculation of those ensemble averages was really beyond their technical means. So there were lengthy and difficult papers involving lots and lots of uncertain and uncontrolled approximations. So it becomes difficult to draw specific conclusions. So one of the questions that people were interested in that era, 30s to maybe 30s to 80s, was the question of, does the solid liquid melting line end in a critical point like it does along the liquid vapor line? And long before, even before that, Bridgman, based on the results of his experimental measurements, had proposed that all substances would freeze at sufficiently high pressures. And there were some models from OK. Rice, which involved random packings of glass spheres. And what he noticed was that the random packings of spheres have significantly lower density than the close packed crystals, which suggested that there could be some transitional rearrangement which would take it from a random packing to a close packing. On the other hand, I think the only basically viable theory of liquids in that era, which could be readily calculated, was the Lennard-Jones-Devonshire cell model, and that predicted a second order phase transition, which would imply that there was a critical point. So there was a lot of discussion and a certain amount of confusion as to what the actual situation was. So then in 1941, Kirkwood and his student Elizabeth Monroe basically used the thermodynamic integration method that Kirkwood had developed earlier to calculate the free energy of the solid and liquid phase. And as a result of their calculations, they predicted a first order transition. This was for the Lennard-Jones system, and no critical point. So on the other hand, Alder and Jura, a little bit 10 years later, claimed that there was a critical point, and their calculation basically matched internal energies and pressures and looked for intersections along the temperature where the internal energy of the two phases matched and the pressure of the two phases matched. And that intersection indicated to them a critical point for argon, for example, at around 1840 Kelvin. The problem was that the theories were all inconclusive because even if the basic underlying idea was sound, the actual calculations required a lot of approximation, so you could never be sure of what it was, what the result actually was. So then we can ask, why hard spheres? Why were hard spheres so important? And the first reason is that the attractive forces have really little effect on the structure of a liquid. And this is summarized in this comment by Rowlandson from 1970, but it was well known even when I was a PhD student that the repulsive interactions were what determined liquid structure. And this was a foundation for several successful perturbation theories based on repulsive force reference systems. And then, of course, Dan extended that very elegantly to non-spherical particles, showing how the actual shape of the particles was critical in determining a lot of their structures and properties. So if it's repulsive forces, then you could roughly imagine liquids as basically being a packing problem. And this was an alternative route to understanding liquids because the formal statistical mechanics in terms of the BBGKY hierarchy was really, really hard. And there was no convincing theory of liquids even after decades of work. Lots of approximation, superposition, Perkusiewicz, hyperneted chain. But this comment from Simon, I think, is fairly appropriate. We really had no better guide than inspired phenomenology. And the inspired phenomenology, or one aspect of that was J.D. Bernal's modeling building efforts, which extended actually over 30 years, beginning with attempts to understand coordination based on the X-ray diffraction patterns from measurements of liquids. If you're interested in that, there's a very nice review article by John Finney, who was a student of Bernal's. So here are just a few pictures. This is from Finney's review article of some of the efforts that Bernal went to try to understand liquids in the era before computers. So if you find sometimes working with computer programs frustrating, then just think of the alternatives and be grateful. So this is Bernal. The first picture is Bernal in the sort of classic X-ray crystallographer mode of trying to build models of a liquid by just joining the balls and spokes together with something like the right local coordinations. And the randomness in this particular effort came from the fact that he did it in his office and was being constantly interrupted. And after each interruption, he could never remember what he'd just been doing. So it was more or less random. And then the second image is him trying to do the same kind of thing in a more controlled way. So here the randomness is introduced, but from actual tables of random numbers, and working from those tables, he positions the strings and the heights of the balls on the string. So he basically has a random array of points. And then he tried to swell it. So the swelling that we will do on the computer is what I'm showing down here. We start with a random array of dots, and then we start to make them bigger until they get stuck. Now, of course, if we were doing it on the computer, we would basically be moving things around in a Monte Carlo way. So it would become more like a thermodynamic process. But what Bernal was doing here was something much more like a random packing, where he's just moving the ones to contact and just doing that over and over until everything more or less gets stuck. And then here is another idea where he took plasticine balls, covered them in chalk so they wouldn't stick, and then put them in a bag and sucked all the air out of the bag so that the balls all get crushed together. And then he'd take them out and unpeel them, and they're basically making the Voronoi polyhedra. And what he noticed from this was that the polyhedra were most of the faces had 5 edges. Many of the faces had 5 edges. And from that, he realized that there was no way that you could pack such a structure into any kind of regular form, implying that the liquid state was fundamentally different from the solid, that it wasn't just a blurred out solid as you might expect from, for example, the Lennard-Jones-Devonshire cell model. And then probably this is his most famous work, and the one with the most long-term influence, was where they did experiments with steel balls. So they pack steel balls in molten wax in a bag, tie the bag up tight so that the balls are packed together, wait for the wax to harden, and then take it out and measure the positions of all the spheres with a traveling microscope. And then they just peel the layers of spheres off one by one, measuring all the coordinates. And many years ago, I visited John Finney, and he showed me the experimental setup. And it was also unbelievably tedious to get this radial distribution function. But nevertheless, this random packing of ball bearings gives a radial distribution function that is a reasonable close facsimile of the experimental measurement from Argon. And it's also reasonably similar to the radial distribution function that you get from a hard sphere molecular dynamics. So these could be thought of as essentially prototype simulations. And then the next sort of part of our story is the question of whether hard spheres freeze. And this is connected to the solid liquid critical point question, because hard spheres can be thought of as a limiting case of a soft interaction at high temperatures and high pressures, where you're basically only exploring the steep repulsive part of the potential. So the question comes for hard spheres is, how is it that they freeze? What's the driving force? Because there is no latent heat here. So if hard spheres are to freeze, then it means that the entropy has to go up when the thing goes from disordered to ordered. So this is, of course, counterintuitive. It's correct, but you can only show it's correct as a result of a complex many-body calculation. So there was not a definitive answer to that question for many years. There were a lot of approximations and a lot of hints. So here was I think the first journal published simulation results, which is a simultaneous, no, not the first simulation, but the first published results of a phase transition, which was a joint two papers published back to back by Alder and Wainwright using molecular dynamics and Wood and Jacobson using Monte Carlo. So in the computer simulation, one new thing is that now the density is variable. It's something you can control, unlike Bernal's experiments. And also we've now introduced the notion of thermodynamics as opposed to random packing. And what they found from both Monte Carlo and molecular dynamics was that the phase diagram for hard spheres had two branches. So if you imagine that you start off at high densities or small volumes, and you gradually expand the solid, you come down the solid line. And then when you get into this region, if you run long enough, from time to time, you'll see that the crystal melts and it becomes disordered. So and then you then track a different branch of the equation of state. And if you try to reverse it, then what you find is you go back up an entirely different pressure line. So you're identifying both a solid branch and a fluid branch, and then this sort of fuzzy region in here where you could observe melting, but not recrystallization. You have to run bigger systems for much, much longer in order to see the system recrystallize. However, this was really quite a bombshell in the statistical mechanics community, because it showed for the first time that you could, by using these numerical simulations, you could identify really new physics and clarify things that were at that point in time unclear. And so these insights from this hard sphere melting problem were instrumental in establishing the worthwhile and value of simulation methods. However, there is a problem with just trying to observe this coexistence directly, is that it's a long way from the thermodynamic transition. So if you just look at the system, it would seem like it was melting somewhere around here, but the actual thermodynamic melting line is in a completely different place at a much higher pressure and a much lower solid volume and liquid volume. And so what we have here is basically the regime of mechanical stability, and the thermodynamic transition happens much sooner. So this was not enough then to, Alder and Wainwright and Wood and Jacobson were not enough to establish the thermodynamic phase transition at all. And so that was first done about 10 years later by Hoover and Ree. And there they went back to the Leonard-Jones-Devonshire idea and used this single occupancy cell model. And so here what happens is the spheres, the black circles, interact with one another through, in this case, hardcore interactions. But their centers are also confined so that they can't move outside of this Wigner-Seitz cell. And based on the results of Leonard-Jones and Devonshire, they were then expecting that this single occupancy cell model would either not have a phase transition or at worst have a weak second order phase transition. So they then use that idea to integrate the single occupancy cell model from high density to low density and compare that with the unconstrained system. So from that, you could get the difference in free energy, just for example, by integrating the volume with respect to pressure. And then there's a correction which accounts for the difference in free energy between the unconfined ideal gas and the single occupancy cell ideal gas. So doing that, they were able to locate this first order phase transition with a specific transition pressure and coexistence volumes. So this single occupancy cell idea, you can use it for hard and soft forces. There's no need for a harmonic reference state. And it's capable of giving really accurate solutions, as we shall see. However, there is this cusp in the equation of state, which comes at the point where the solid is no longer being held in place by interparticle interactions, but it's now starting to be held in place by the cell boundaries. And that makes this kind of phase transition here, where there's a cusp, which suggests that it may not be so accurate to try to integrate your way through that cusp. So if we were going to apply this, so our thought at Cecam was that we could basically improve on the Hoover recalculation by using this Einstein reference, because we imagine then that there will be no issue with any kind of cusp or any kind of irreversibility or hysteresis. So the difference in parameterization now is that we can no longer turn off this hard sphere interaction. So we don't have a kind of integration from 0 to 1. We basically have to go up to some large value of the spring constant so that the particles are so tightly bound to their lattice sites that at typical volumes of the solid near melting, interparticle collisions are very rare. And then to account for those interparticle collisions, we used a virial expansion. So the idea here is that you never have more than 2 particles overlapping at once, and that those overlaps are really quite small. And then using a cluster expansion, we get a formula like this for the correction to the free energy. And this P is basically the overlap probability for 2 neighboring Gaussians with a width that's proportional to 1 over the square root of lambda. So then we have to actually calculate the difference in free energy, which means integrating the potential energy of the spring system from lambda 0 to the maximum value we chose, which was something of the order of 600 or something like that. But the idea being that you make lambda big enough that the mean square displacement is really small. And one important point was that we need to fix the center of mass in order to suppress the otherwise large fluctuations that would occur as the spring constant goes to 0. Because if the system can move its center of mass, then you basically have a system of a spring with the spring constant going to 0, which gives you diverging displacements. So that would not make the integration very, very good. So we impose a fixed center of mass. And then there are 2 limiting cases. When lambda goes to 0, now the potential energy goes to some constant, whereas if lambda becomes very large, it goes as something like 1 over lambda. So what we did was to multiply it by lambda plus c, which then means that the potential energy or the mean square displacement varies quite smoothly and not very much over the whole range of spring constant, the whole range of lambda. And you can see here that the squares are basically what we get from the Monte Carlo calculations at different values of lambda. And this is the overlap approximation. And you can see they're pretty close, though not exactly the same at the highest value of lambda. So in these calculations that we did at Cecam, really we didn't use quite large enough a lambda to make the mean square displacement small enough that the free energy would, that the correction to the free energy would be really precise. So then we were able to calculate at the workshop the free energy of the hard sphere system for different numbers of hard spheres, 32, 108, and 256. And it seems to extrapolate really quite nicely, oops, to a value of about 5.93, which was pretty close to Hoover's and Ree's value of 5.92. So we were encouraged by that. But it turns out it wasn't quite so simple. So one thing that we had overlooked was what happens to the Einstein solid when you apply a center of mass constraint. And we had applied something as shown in this line here, whereas importantly, it needs to be divided by 1/n, which is the Fourier transform of the delta function on the center of mass. And this basically affects the metric that you use to do the integration. So the net result is if you don't put this in, if you use this form for the center of mass constraint and do nothing to the momentum constraint, then you land up reducing the or overestimating the free energy by 3 log n over n. And then there was another thing that we overlooked, which was the difference between the configurational integral of the unconstrained and constrained system. The real answer is V over n because it's only over the Wigner site cells, and we took it as the whole volume of the system. So that means that the free energy is actually reduced by 2 log n over what we calculated. And so in the plot here, I'm showing basically the data that we got from the Cecam workshop and immediately afterwards. And then if you subtract 2 log n over n, you can compare it with the much more recent results from Paulson, and it lines bang on their line. And so this log n over n term here is actually the correction that Hoover observed in harmonic crystals. So a finite size harmonic crystal has a correction of order log n over n, and Paulson et al. Assumed that it might be the same in hard spheres, and their data shows that it very much is. And from that, they could get an insanely accurate calculation of the free energy of the FCC structure. So then after Cecam, we had decided during the workshop that what we were trying to do is calculate the free energy difference of the hexagonal and face-centered packings. But despite our best efforts, we could not actually get a statistically significant difference. So we were careful to choose structures that enabled us to run for the same number of particles for both structures, which was very useful since we hadn't accounted for the n dependence entirely correctly. So by using the same number, it would just cancel out. So, but nevertheless, it was not enough to get us to statistically significant difference. But we could be fairly sure that whatever it was smaller than 10 to the minus 3. And then in 97, Les Woodcock published a paper with a much larger difference that was considerably outside our error bounds. And that provoked Dan to recalculate it with 2 different methods. With Peter Bolhuis, he calculated using the Einstein crystal method, and then it was also calculated using multi-Hamiltonian methods. And both methods gave more or less the same answer of that the FCC phase was more stable by a very small amount, about 0.001. Later, Les reworked his calculations and found still a larger value, but now more or less within the error bars. So the final result after many years of work is that FCC is marginally more stable, although that's probably pretty irrelevant. And let me just mention one. So as I was working on these slides, it occurred to me that we were always calculating Helmholtz free energy, and really what we want to know is what the Gibbs free energy difference is. And I think, always made the assumption that the pressure corrections would be really small because it was hardly observable in the molecular dynamics of the day. But if you actually calculate what P delta V is, so this meaning the difference in volume of FCC and HCP structures, at the transition pressure, it's small, it's 0.0009, but it's the same size as the delta F. But in order to make this correct, you also have to take into account the fact that whatever reference volume you calculate delta F as, you have to convert that to the volumes of the two crystal structures at that pressure. And in the case that we were working with, we basically took the reference volume as the volume of the FCC phase. So then you land up with an extremely small correction because you're talking about a very small volume difference between FCC and HCP. And you're talking about a very small pressure difference between the pressure of the HCP phase and the reference pressure. So those things together give you a very, very small correction that's still an order of magnitude less than the Helmholtz free energy, so that it's perfectly okay to ignore that. So just to summarize then, I would say that the Cecam workshop was really crucial to developing thermodynamic integration-based free energy methods. So there was a real focus at the workshop on discovering new things and also on resolving difficult technical problems. And that was done with a lot of discussion and a lot of collaboration. And we should definitely recognize that that roundtable discussion on a more or less entirely different topic was really crucial to stimulating our thinking. So my thanks to Dan and the other Cecam participants, and thanks to Ignacio and Sarah for this trip down memory lane. So thank you all for listening.
Okay, Tony, thank you very much for this presentation. Very clear, and I think it provides a very nice historical perspective into the subject and what lies behind this thermodynamic integration algorithm. Now we have a few minutes for questions and discussion with Tony on his talk. I remind you to all participants that you can pose your questions by using the Q&A feature of Zoom. You have to write your question or your comment, and I will relay it to Tony. So we have one already by Bim All saying, did you ever use entropy instead of free energy to calculate and measuring the stability of the system?
I mean, so I'm not quite sure what the question is probing at there, but because I mean, for hard spheres, the entropy is the same. There is no energetic contribution. But in general, I mean, the thing that you really want to know is the Gibbs free energy at constant pressure, because that's what controls which phase is the most stable.
Mm-hmm. Is this something you did in the workshop itself? I mean, already addressing the issue of the Gibbs. Yeah.
So that plot that I showed for the free energy of the FCC phase was what we did in the Cecam workshop, because Dan already had the Monte Carlo program, so we were set up to do that. Though that was a cubic box, which is not suitable when you want to compare the FCC and HCP, because you have to have you have to stack the close packed planes in order to have the same number of particles in both phases.
Mm-hmm. Okay. Another question by Martin Hurin. I think that's something that probably will come up later in different cases, but it says, if I understand correctly, you perform these calculations with Dan at the workshop. Practically, how did this work back then? Presumably, you didn't have laptops with you.
No, we had the awesome computer facilities of the OSE computer system. So, in fact, one of the attractions, and I think probably one of the reasons why Carl put Cecam at that place, was that at the time it had one of the most powerful supercomputers in Europe. The downside was that the main interest of the computer staff at the system was translating IBM JCL into French. So they were always too busy to help you because they had to work on their translation. And it truly did need some work, because it was just a horrible mixture of French and English. So it would prompt you in French and you would have to type the reply in English because they hadn't got that far yet, or vice versa. So I think by the time they finished, IBM JCL had been dead for decades. But yeah, so there were computers there, and you would you would bring your stuff on magnetic tape because there was no email. So it took a fair bit of preparation if you want to be able to get work done, but it was definitely possible.
Okay, so we have another question. This is by Patrick Warren. He asked, should one worry about vacancies with this SOC type or Einstein reference crystal approaches?
I mean, clearly there are vacancies now.
Can I answer that question? Because
yeah, go ahead, Dan, because you've thought about that. Yeah,
no, we did it.
Okay.
So
That's even better.
no, actually, so much later, we did compute the free energy of a crystal, including the vacancies. And if you allow for vacancies, the free energy goes down a bit, but it's a very small amount, but it's measurable.
Mm-hmm.
But certainly in 1983, no way.
Okay, thank you. So there is another question by Christopher Dow. I was wondering if you would mind going even further back in history and relate this to the work of Kepler, etc., on sphere packing. I don't know.
No, okay, that I'm not that old. Okay, so I don't remember that.
Okay, but
No, I'm not familiar with what Kepler did. Was it regular packings or random packings?
I don't know.
It's the regular packing. I mean, Kepler was the one who assumed that this was the densest packing.
Okay.
And then for 2D, Gauss showed it of course, in the 19th century. For 3D, it's only at the end of the last century that was proven.
Okay, cool.
Okay, so then there is a question by Bill Curtin. He says that since the FCC and HCP are extremely close, he asked whether the true thermodynamic ground state is actually a random sequence of A, B, and C stacking planes. He says that seems like the entropy of mixing outweighs the FCC-HCP difference.
Yeah, I mean, I think we had considered that. We had considered that possibility. So I'm just trying to think off the cuff.
Can I say something? Because again, it's something that so the thing is that if you have a small crystal, it always has these stacking faults. But if you go to the thermodynamic limits, the free energy difference between HCP and FCC scales with the system size, so scales as n, whereas the stacking fault entropy, because you have to do it in one direction only, you can't have that scales like the 2/3 power. So in the end, in thermodynamic limit that you probably never reach, it would, the stacking, the random packing would not be important. But in any colloidal system that people study, you always see stacking with some degree of randomness.
Mm-hmm. Yeah. Yeah, it's similar. It sounds similar to the questions of Ising model in 2 and 3 dimensions, 1, 2, and 3 dimensions. But okay.
So Eric Lawton says that this is a wonderful summary of the history of these models. And then he asked, does the difference between the free energies of the FCC and HCP lattice change and maybe even reverse if the particles are not hard spheres but have an additional attraction? He says, after all, it is not obvious that the enthalpy is identical.
Right. No, I think it's not. It's not obvious. What I remember is that for Leonard Jones, the FCC is more stable, also, but I think a more significant amount. But that's just a recollection. I think in general, you know, the noble gases are FCC crystals.
Okay. So Ping Mao asks, will you elaborate more on the part you mentioned regarding attractive forces have little effect on GeoPar? Because experimentally, if we think about the hard sphere colloidal system in liquid, if you have more attractive forces, you will have more first neighbors, which means the first peak in GeoPar will be more profound.
I mean, I think yes, but those are small quantitative differences. You know, you got to remember the accuracy to which people were working in that era. I mean, so they weren't measuring tiny differences. But I mean, if you look at like Bernal's G of R compared with Argon, they're remarkably similar. So the first peak is higher. So the Argon peak is a bit more rounded, but you know, in terms of understanding the basics of the liquid structure, that's more or less, more than you really need. So it's perfectly good, I think, to imagine hard spheres as a reference. You can then, of course, add soft interactions as a perturbation, which is the Barker-Henderson or Weeks-Chandler-Anderson idea.
So there are 4 remaining questions. I'll try to go through this if we can, relatively, without delaying too much, but I will not accept more questions because otherwise we will just be too late. Since there is the conversation section at the end, there may be also questions that come up at that part of the event. So the next question is by Zili. He says that Navasquez and Velasco in 2010 proposed a different scheme for the fixed center of mass correction. Will different correction scheme affect the relative stability of FCC and HCP?
I mean, it should not, right? Because you basically have to make sure the reference system is using the same constraint that you're using in your actual simulation. Now, I mean, just to note that, in fact, when Hoover did lattice dynamics, he would also fix a particle, not the center of mass. And that was just purely expedient that you've got a force constant matrix which has singular eigenvalues. So if you don't want to try to diagonalize it, the simplest thing to do is to just cross out the rows and columns of one particle and then just calculate the determinant of that matrix. So that idea of fixing a particle rather than fixing the center of mass also has a little bit of history.
So Tapio Rantala goes in a different direction. He guesses the 0-point motion and other quantum effects are negligible in this kind of simulations.
Well, of course they're negligible because they're not in the equations of motion. So yes, whether they're really negligible, of course, is another question. But as far as the simulations are concerned, they're definitely negligible.
So Bill Curtin has a second point. It's more a comment. He says that as a historical note, his thesis advisor, Neil Ashcroft, told him in 1986 about the first MD of hard spheres freezing by the English physicist William Sunderland around 1893. And he said here the MD is marble dynamics, quote. He shook a container with clear marbles and one red marble and looked for the density at which the red marble could not diffuse. Might have been random close packing, perhaps. I mean, again, I don't know if you were aware of that.
I'm not aware of that calculation. So, but I mean, what would happen? So the things being so the things being shaken. I mean, I've seen gas phase examples of that at a science museum, basically an agitator plate. So I'm not sure how I guess the thing must be being shaken. I don't know how you would shake it hard enough to energize it when it's dense, because the collisions are relatively inelastic. But okay, that's I'm not aware of that one.
Yeah, it's also going back in history. Yeah. And then also just to close it with another historical note, Mike Allen just said that he just wanted to say thanks for this very nice talk and for reminding him that he was there also. Yeah? So.
He was. And we just a final comment then, since he commented, was the enjoyable walks around Paris trying to find a vegetarian restaurant. So, in the early 1980s, that was not an easy task. But it was an enjoyable one anyway. So,
okay. Well, thank you very much, Tony. Thank you, everybody, for the questions. I think we should stop here in order not to delay this too much. Since we are a few minutes past 4, I think it's appropriate that we reconvene 4:15, so that we have the time to refresh a bit, and we will then start with the second presentation by Dan. So see you now in a few minutes. Hello, welcome everybody back after this short break. We will now move to the second presentation of this afternoon, delivered by Dan Frankel. So now, please, Dan, Floor is yours.
Thank you. Let me just first try to share. Yes. You see it?
Yeah,
Always.
I see
Okay,
it.
perfect. Well, first I'd like to thank Cecam for allowing us to give this talk. I'd like to thank Tony for covering much of the ground that I now don't have to cover. Actually, we knew that beforehand, but I will also say that during my talk, I will come back to some of the things that Tony mentioned, just for the sake of continuity. And the other thing I would just as a comment is that Tony mentioned that indeed workshops at the time were much longer at Cecam, and there's a huge difference. It's almost completely inverted from the way it was now, because then people would come to Cecam and they would be completely cut off from the home base. There would be no email, of course, because it didn't exist. Phone calls were ridiculously expensive. So for people who had to rely on the occasional letter, and now we have a workshop or a Cecam activity, we're not even at Cecam, we're only communicating electronically. So that shows how things go. Anyway, what I want to say is a bit about what happened with free energy calculations of solids afterwards, but I should also say that that's essentially an impossible task. So it is a bit biased also by my own experience, and you have to forgive me for doing that. The one thing I do want to say though is that the Cecam workshops were incredibly important. Sorry, I have to remove this. Go on. Were incredibly important for the development of computer simulations in Europe, because these long workshops were the places where the generation of people who were subsequently developing and expanding simulations in Europe received their training, and that cannot be overstated. I should also say that I had been at Cecam before 1983, and actually when I was a PhD student in 1975, I spent 5 months at Cecam. It is like not quite as long as Jean-Paul Ricard or Giovanni Cicotti, but it was a fairly long time. And so this is, let me see. Oh, I have to also do the pointer to make it look like a laser pointer, which of course now immediately it stops doing. I don't know why that is. Anyway, sorry, I can't. This is the same picture. This is Carl Moser. Probably it's just a few years, 2 years later, in his office with his dogs that were loved very much by him. I was there as a student, and so I actually have a picture of me in Paris. What I actually will show you is a short movie that actually is on the Cecam archive of Carl Moser. This is at an event a few years later where we were speaking, and if it's all right, you should be able to hear something, but I don't think you hear anything at all.
Not hearing, no.
No, I mean, that's interesting because I did share sound, but it doesn't work. Anyway, that's Carl Moser. Let me go on to the next, if I can somehow convince the thing to move. Gosh, yes. And this was me at Cecam in 1975. And just to give an impression of the workshop, you might think that during these workshops, much of the work was done, people sitting in these offices and talking. Well, actually, they were talking and they were sitting, but much of the interesting discussions were somewhere else. They were actually in the evenings in Paris when we were having a glass of beer. This is a bit later, but this is I think this is 1989 where we were sitting and, well, I mean, I will not name all the people who were sitting there, but I could tell you if you're interested. So this combination of formal and informal contact made Cecam such a fantastic place to be. Now, for me personally, coming to Cecam in 1975, there was a few things that were like a culture shock. The first thing is that at that time, and this is something that after more than a year of pandemic you can't quite remember, is that if people of the opposite sex would meet in France, then you had to kiss. But the question is how many times and on what side. So actually it's non-trivial because there's a map of France where apparently people kiss on the right in this part of France and on the left in that part. And then the other crucial question is how many kisses? And again, there's a difference. 4, this is roughly around the Paris area, but maybe not completely. So it could also be 2, and here it's 3, and then actually only in the extremely almost Calvinistic parts of France it is 1. These things you had to find out. And actually, it seems that it's not even a rock completely solid, because it also depends on age. But that was, for me, an important learning experience. But even more importantly, Cecam at that time was housing a large Italian community, names that you still know, like Giovanni Cicotti, also Gianni Iaccucci, Vanda Andreoni. And so one thing I had to learn is Italian ways of communication. And so I would say it's Italo-English words of communication. And I couldn't find, of course, pictures from the time itself, because we didn't take pictures, actually. I mean, like this idea that you have your mobile phone and take snapshots of everything is rather modern. So, but you have to know that if you communicate in a group with many Italians, that words are only part of it. It's the gestures also. And so this lady, by the way, apart from Vanda Andreoni, there were not many ladies. So the gender balance at Cecam was very skewed, to say the least. But this is one. What are you talking about? I'll come back to the text in a minute. This is a gesture that is supposed to say "go to hell." This is the text that says "you are boring," and this is "are you crazy?" Now the thing is that the way I learned it, I cannot. These texts are totally irrelevant because that was not what was being said. But the thing is, I can't repeat it. So the thing is, what are you talking about? I just well, I could have left a few letters in, but not much. The Italian gesture for "go to hell," actually, the text actually is quite different, and it is this. The other two I can just about translate. So "you're boring." This is there's two words that Giovanni Cicotti used to use. He would call people boiled fish or crocodiles if they're passive, and then if people are crazy, then they would call them a madman. So these are the things you have to understand in order to be able to communicate in that environment. But apart from it, it was absolutely wonderful. Good. Coming back to free energy calculations, Tony mentioned the Hoover-Ree method to compute the free energy of a hard sphere solid and also hard disk solid using this single occupancy lattice model. And not long after that paper was published, Jean-Pierre Hansen, who is, as far as I can tell, even watching now, wrote together with his supervisor Lou Verlet a paper on the phase diagram of Argon, of actually Lennard-Jones Argon, but that paper certainly contributed hugely to the popularity of the Lennard-Jones potential, because it really did reproduce the phase diagram, the experimental phase diagram of Argon very well. And so here you see actually the phase diagram as published in that paper. And but the phase diagram also contains the points, the data points from the experimental data on Argon by the group of Michels in Amsterdam. So this was a major victory of simulation to be able to get essentially quantitatively correct data for phase diagrams. The only area where it doesn't work for these small systems is close to the critical point. But this Hansen and Verlet were well aware of, and they basically say that you can't expect it. Now, the other thing is that they did use the single occupancy cell method, and Tony already mentioned that there's an issue, and the issue is that there is this liquid gas transition in the cell model, actually the point where the constraints are no longer effective in localizing the cells are no longer effective in localizing the particles. And they write there seems to exist a second order phase transition at the density about 10% lower than melting. That's what Tony also said. This was based on the Lennard-Jones Devonshire argument. But actually later there was a Japanese group who looked in more detail at this same phenomena. This is the group of Ueda and others, Ogura. There are actually quite a few people involved. And in 1977, they looked in more detail, and they actually concluded, this is a very strange way of plotting, but effectively it's the pressure but it's PV over NKT. They plot the compressibility factor as a function of density, and they argue that actually what you see here is not a continuous phase transition, it is actually a first order phase transition, which therefore may have hysteresis. So this was one of the reasons why when Tony and I were working on the problem, we were already sort of worried about the single occupancy cell model, and I think there was every reason to be worried about it. And this is the other thing that Tony also said, if you have systems with continuous potentials, then there's very often the alternative that you can use to compute the free energy, and that is to use the harmonic solid as a reference state. So it is not that you assume that the crystal is harmonic, you just assume that at sufficiently high densities or low pressures, temperatures, you get to a harmonic solid if you don't cross the phase transition, and then you can use that information to transform your real crystal into a harmonic crystal. And that was actually already in a paper by Bill Hoover and a whole lot of other people in 1970. Now, just the harmonic approach has a big advantage, and that is actually that you don't have to know very much. Certainly, with modern day computer, you may think, oh, I have to solve the harmonic lattice calculations to actually work out what the partition function is and then get the free energy. But actually, the only thing you need, except for all these boring factors, well, this is the potential energy, but you only need the frequencies of the different normal modes of the crystal. And the thing about these frequencies is that you get those simply if you compute the Hessian of the system. So if you have the Hessian, you have all these frequencies, and you can compute the harmonic partition function, and that's it. And so that was extremely useful. And I should say that actually Jean-Pierre Hansen also then redid the Lennard-Jones solid calculation using the harmonic lattice reference state, just to show that although they had used the single occupancy cell method before, basically the answers were correct, because the harmonic lattice reference state is of course something where you can be a bit more certain that you do it right. Now, I show this because it shows something. I'll come back in a minute to this other thing that it says comment on, but I first want to say something about where the harmonic method works and where it doesn't. And so, because this is a line in the article, and there you see here the free energy, and this is the harmonic free energy. So here you see density, it's at constant temperature, the density goes up and up and up. And here you see the harmonic free energy, and here you see the real, I would say the free energy that has all the anharmonicity in it. And the main thing is that if you go to really high densities, and no, not really, not excessive, if you go to high densities, it works extremely well. But if you're at low densities, then the harmonic approximation, although not awful, is clearly wrong. So, but it shows you that if you can get away with a harmonic lattice calculation, that is a very attractive option. And I mentioned this because in my talk I jump back and forth, and so now I jump forth. This harmonic approach has been extended quite a bit in recent work by Binchen Cheng and Michele Ceriotti, who of course point out that the harmonic approximation can give you inaccurate and qualitatively wrong results, but that you still can use it as a reference method in simulation. If you, for instance, take a system and you bring it to high pressure, high densities or low temperature, and then look at the free energy difference between that and the harmonic lattice, that is a very good thing. And the point is that in that case, you don't actually even do a thermodynamic integration. You use an expression that is just perturbation theory. So you just say, the free energy of my real solid is the free energy of the harmonic solid, and then this term, which is basically the potential energy difference between a real solid and the harmonic solid at the same configuration, and then averaged. And so this is a particularly easy recipe, computationally easy to implement, and based on this earlier harmonic solid like calculations. But I had said that I would come back to the Hansen and Pollack calculation, where they had something that was a comment on the Monte Carlo studies of the fluid phase transition in a Lennard-Jones system. And so I mentioned this because there were many different approaches suggested at the time about how to locate a melting transition. And so this comment by Jean-Pierre and Roy Pollock was commenting on the following article. It was an article by Bill Street, or Street, Ravachey and Mountain, who actually said, well, if you take a simulation of a, well, whatever system, it could be Lennard-Jones or something else, hard spheres, and this is the volume, this is the pressure at constant temperature. If you compress it, at some point spontaneously, it will freeze. If you take the solid and you expand it, at some point spontaneously, it will melt. And so the idea was that this volume was relatively well defined. And then they said, well, what you do is you just make a Maxwell construction. So you make this area equal to that area, and that leads to an estimate of the coexistence densities of the coexisting volumes. And that is actually something that doesn't work. I mean, if you remember the picture that Tony showed for the hard spheres, the main problem is actually that the point where the solid becomes, the density where the solid becomes unstable and the density where the liquid freezes spontaneously in the simulation are not at the same point. And actually both points, in particular the one for the liquid, are not at all well defined. They're strongly system size dependent. But in a sense, this method has been revived, and I should be a bit careful. It hasn't really been revived, but it has come back under the name the Zeta Method. You can imagine that this looks like a Z. So that's what the Zeta Method was introduced in 2006. And it does something similar. It says, take a system of an atomic crystal, and then you just increase the energy. These are constant energy calculations. And at some point it melts. And then they say, once it is molten, the density of the liquid in that system is actually the density of the liquid at coexistence. And first you think that that's a very strange statement, but actually there's a good theoretical reason for this, why this could work in principle if you have a large enough system and you have enough time to let the thing equilibrate. And the reason is that basically what you have is you have a system that is at constant energy, and when you melt the system, the energy, the temperature changes, but then you end up in a two-phase region. You have the density was that of the overexpanded solid. You get then a coexistence between a solid and a liquid at a different temperature, but it's an honest to God coexistence, except of course that there are huge finite size effects. And how huge these finite size effects are was shown in an article a few years later by Mike Gillen and Alvar Cazorla, who actually compared the free energy calculation result for a phase transition. I forget what it was, probably a metal, knowing that one, but possibly iron, I can't quite remember. And this is what you get from a free energy calculation with, and this is from the Zeta method. So I would say it is in the same area, but it is certainly not something that you would try to use if you want to have an accurate estimate for coexistence. But again, the reason why this method has at least some justification is really that what they see is this direct coexistence between solid and liquid, and necessarily at that point the liquid has the density of coexistence. So that is an interesting development, but personally I would never use this method. What Tony did not tell is that he had been involved actually together with Les Woodcock in another method to compute coexistence, which is the one that everybody would think of immediately if you're thinking about freezing. And that is actually to prepare a solid and a liquid directly in coexistence. Actually, Tony and Les Woodcock were much more ambitious at the time. And remember, this is in 1978 when is the time of the steam computers that were running backwards. They said we want to see the solid coexisting with the liquid coexisting with the vapor. And the problem is that these calculations, well, first of all, it didn't work very well. And there's two reasons for it, why it's very difficult. One is that the small system sizes make that there is a huge effect of the interfaces on the location of transitions. The finite size effects are really dramatic, and the other thing is that to get these things to equilibrate takes forever. And so this is why at that time this method didn't go any further. But again, if you then scroll forward, you find that although it was tricky for these small systems, with current computing power, it is not such a bad idea. So this is the group of Carlos Vega, who has been looking at using this direct coexisting systems method to determine phase diagrams, and they write, although the initial results for the Lennard-Jones and inverse 12-power system were not very successful, probably due to the small system size, the method has become much more popular in the last few years. So basically, this is one of the methods, in a sense, has been revived by just simply the growth in computing power. I still want to add a word of caution, because if you want to do this direct coexistence calculation right, you have to be very, very careful. And the reason is that you want to prepare the system in such a way that the solid indeed has the correct properties that it needs to have to be in coexistence with liquid. And you say, yeah, well, of course, that's what you need. But if you have a system and you prepare a solid and a liquid that are initially in contact, and you change the temperature or the density in such a way that the interface doesn't move, you have to change the pressure of the system. And almost certainly that would mean that the solid wants to adjust its lattice parameters. But if you have simulation boxes with a fixed shape, then they can't do it. And so the solid is actually a stressed solid and therefore less stable than the equilibrium solid. And there's all kinds of subtleties that Carlos knows very well, but that you have to be aware of when you use this method. Okay, so this is just a renewed introduction to why there was a need for a reliable free energy system method for hardcore systems, for which there was basically no other reliable method, because the harmonic lattice approach wouldn't work. And there was also a scientific reason for doing this, and that was that these models, these hardcore models in the 1950s, people said, well, we can't do real fluids, so let's take very cheap models for fluid, namely hardcore, the hard spheres. But people always thought, well, that's actually a poor man's atom. But by the 1980s, experiments in colloid science had progressed to the point where it was actually becoming possible to make colloidal suspensions of particles that really behaved like hard spheres. That is the famous Pusey and Van Meeghe experiment that actually was a bit later, but also Agnes Vrij was working on these systems. You could make colloidal suspensions of particles that would not attract or repel at larger distances. They just would have extruded volume. And these systems, I mean, so you first, you could at some point start comparing with the freezing and melting of hard spheres, but later on, it became possible to very systematically study the phase behavior of non-spherical hard particles, which is something that was of much interest to me, because I worked at Utrecht at that time, and in Utrecht there was and is a very strong colloid chemistry group and colloid physics group who were studying all these systems. And with the Einstein crystal method, it was possible to actually approach this kind of problem like hardcore models of non-spherical particles, because the hard spheres, you can say it's conceptually interesting, and it was of course important that you can compute the difference in free energy of FCC and HCP, but as Tony said, as such, the number has no fundamental importance whatsoever. So it's not that was a burning problem that influence was, whereas the phase behavior of non-spherical particles had much more implications for other fields. Now, again, I will, as I said, sometimes I come back to what Tony said, and so here I come back to what he said about the Einstein crystal, namely that this whole idea of thermodynamic integration, of changing the Hamiltonian of a system, is old. It is indeed due to Kirkwood in 1935, except that, so this is the article by Kirkwood that Tony also showed, but actually Kirkwood in his article referred to something else. And what he referred to is Onsager. And because the whole idea of thermodynamic integration by changing the Hamiltonian is not immediately obvious. And so Kirkwood says, as Onsager has clearly pointed out, etc., etc. So the parameters that appear in the potential essentially have the same status as the parameters of the external force. And so this was the real reason why Kirkwood started thinking about sort of Hamiltonian, the transformations that change the Hamiltonian. So the whole idea of thermodynamic integration by changing parameters that you can't change in nature, in certain experiments. And so I just dug up the sentence in Onsager, and well, although Kirkwood says, as Onsager has clearly pointed out, I would say Onsager said it, but he doesn't point out anything. He assumes that you just understand instantly that if whatever the parameters are that you use, that you can use this is actually an expression for the free energy change due to changes in all kinds of parameters on which the Hamiltonian depends. And so it is there, but I guess you have to be Kirkwood to immediately recognize the significance. So that was actually, in a sense, again, a disclaimer. The Einstein crystal method as such is not a discovery. It's just a technique that turned out to be very, very useful. Now, what I started doing after we knew that we could do the hard spheres is actually to start looking at other shapes. And so, I mean, I didn't quite get to this shape, although Marjolein Dijkstra subsequently has. But actually, Tony said 1988, with the first calculation we did on hard ellipsoids, so that's the simplest generalization of spheres, is already from 1984. So it really, this work enabled me to do really interesting things, at least what I found interesting. I'll show a few examples of hard ellipsoids, solid mixtures, and then a number of models that showed really different phase behavior, in the sense that they could also give liquid crystalline phases. Actually, the ellipsoids also do that. And so I'll just show you a few pictures and make a few comments on what it meant. So this is what we wrote on, this is with Bela Mulder, on the phase behavior of hard ellipsoids. So basically what you see here along the horizontal axis is the aspect ratio. So one is a sphere. So this is the older Wainwright Hoover rephase transition between the liquid and the solids. But then as you make the particles either more cigar shaped or more disc shaped, you get to a point where you get a nematic phase. That is a liquid crystalline phase where it's not a crystal, but the particles are on average aligned. So that is why they call it a liquid crystal. So there's an alignment, but no translational ordering. And then if you go to higher density, you get the crystalline solid. This is an orientationally ordered crystalline solid, and this is what people call a plastic solid. That is it's orientationally disordered. And that, I mean, without the Einstein crystal method, it would have been absolutely impossible to carry out these simulations. This is another example where doing the free energy calculations was really important. It is the calculation of the phase diagram of a binary mixture of spheres of different size. Now, this is a bit exaggerated to here see large spheres and small spheres. In most cases, the size differences that we considered, and this is with Wilfried Kranendonk, Winfried Kranendonk is less than 15%. So, but the main thing that you see here is that if you take a system, hard particles in a mixture, and you change the composition from being a purely, I guess that in this case, it is, I always forget which one is hard and which is large and which one is small. But if you change the mole fraction from, I think this is the small one, this is the large one. If you change the mole fraction, then this is the fluid. And here you have a solid of large particles with a few small ones, here small ones of particles with a few large ones, and this is a eutectic point. So here you get direct coexistence between the two crystal phases. And this is what we did, is we computed the free energy of the solid, of course, for the pure solid. Well, actually, we didn't, because that was a pure hard sphere solid. We didn't have to do it. And the only thing we had to do is to then do a thermodynamic integration where we change the composition. And this is something that you can do with Monte Carlo swap moves. Then this is another example. This is, I said, Sphero cylinders. Sphero cylinders are, in a sense, have a richer phase behavior than ellipsoids. So here you get now the aspect ratio between the Sphero cylinder of the Sphero cylinders. A Sphero cylinder typically is a cylinder with hemispherical cap, and so the L is the length of the cylinder and D is the diameter of the sphere. So if L is 0, it's just two hemispherical caps on top of each other. And then as you move away, you get more and more elongated things. Like this is a picture that Peter Bolhuis took a long time ago. I think it's aspect ratio 5 or something like that. And so you see here again is the good old hard sphere freezing transition. This is again the plastic crystal. Then at some point that plastic crystal disappeared and you go directly from isotropic to crystal to orientationally ordered crystal. But for larger aspect ratios, so for less spherical particles, you get first a smectic phase. That is a phase where the rods are arranged in liquid-like layers. And then if you go to even higher aspect ratio, but only slightly, you in addition get a pneumatic phase. So you get really now a very already quite a rich phase diagram: isotropic, pneumatic, smectic, and crystal. So that is something that was enabled by all these free energy calculations. Where I should also say that to locate this phase transition, a separate kind of free energy calculation was needed that I will not discuss now. One thing about how accurate you can get, and so I was already mentioning when Tony was asked a question about the whether or not there would be random stacking, that we did the calculation, and indeed we computed, this is a standard Pronk, we computed the cost of creating a stacking fault, so going from FCC to HCP in a crystal, and this gives you an interfacial free energy, so this is per unit area, of the order of 2 × 10⁻⁴ in the appropriate unit. So this is a very, very small number, and that is why you really I mean it is in experiments you almost never see an equilibrium distribution of stacking faults, just because this number is so small, and once a crystal plane has landed, it will not anneal, because the driving force to change its stacking is so small. So you often get kinetic random stacking rather than thermodynamic random stacking. Okay, so now let me just say a bit more about other applications, because I mean, hard spheres are all good and nice, and the non-spherical hard particles are interesting for colloidal phases of rods and disks. But of course, the interesting thing is also to go to molecular systems, and it's somewhat surprising that, to my knowledge at least, the first free energy crystal for calculation for any molecular liquid solid transition was done by Everton Meyer when he was my PhD student, and then subsequently we moved to larger larger molecules like octene and polyethylene. And I will not go into detail, just show you something. I'll also show you how you can make mistakes, and then I'll say finally something about a more recent thing, and that has to do with solubility. So first, the location of the melting point of nitrogen. I mentioned it also because this is 1990, but it actually was done together with Tony, who at that time was mainly interested in lattice Boltzmann calculations and the like. So, but he was willing to get involved in this project, and we used something that it did use an Einstein crystal, but the way we moved from the real crystal to the Einstein crystal was in this case a bit better, but they're different. But that is not really important. So, but it just to show that you can apply this method just as well to molecules as you can apply it to atoms. Then next one is as I said, octane. We did this is maybe 1 year later. We did the calculation of octane with James Paulson, and here I say not everything went right, and so many years later, Bart Forslaers pointed out that almost certainly we didn't treat the symmetry of the molecule in the solid and in the gas phase in the same way, and so that there's an n-log2 correction in the entropy wrong, which does shift the phase transition a bit, but effectively, although the answers almost certainly quantitatively are not quite right, it is just to show that these calculations could be done, and therefore even molecular solids can be studied. The stability can be studied with these free energy calculations. Now, this is I would say this is the point where I gave up. Chinmoy Das did calculations on a short, but not very short polyethylene model. It's C198. It's for me, it's incredibly large, and was able to compute to estimate the melting point, and which was, well, say in good quantitative agreement with the available experimental results. But I mean, the thing is that these results depend so much on the force field that if it agrees well with the experimental result, then I would say only say we must have been very lucky. The last thing I want to say about the Einstein crystal method that we used is that the reason why it's important is that you can compute the relative stability of different solid phases, but possibly even more important is that if you know the free energy of a solid, or more importantly, the Gibbs free energy, then you can compute, or you know the chemical potential of the molecules in the solid, and therefore you can compute the solubility of the solid. And that is a hugely important area. So I had a PhD student in Cambridge a few years ago who did, Luna Lee, who did quite extensive calculations of the solubility of a number of relatively simple, but I mean not totally trivial organic molecules, but she also looked at very different compounds to try to compute the solubility. And I mean, the thing is that it works well, the method works well. I mean, at some point there are technical problems, but the method works well. But we found that force fields that are good enough for pretty much anything else, certainly for liquid vapor transitions, critical point, you name it, they are not good enough if you talk about a solid. And this is something that was already well known from work that Jean-Paul Ricard and also Mike Klein did many years ago, where they showed that if, for instance, alkanes, the longer alkanes have a rotator phase, but if you use the united atom model for the alkanes, you get this whole phase completely wrong. And so in that case, a fully atomistic description, including all the hydrogen atoms, was essential. But it's not so much that the hydrogen atoms were essential. It's just that solids really are sensitive to the details of the force field. And of course, at some point, you can no longer pretend that it's all pairwise additive, and you have to go beyond that. And that's, of course, what people are doing now on a massive scale. But this is just to show what actually the spin-off from the Einstein crystal method. But of course, the more important spin-off is that many other people started computing phase diagrams, including solids. And I didn't quite know how to acknowledge it. I mean, so what I did is something maybe a bit stupid. I just looked at the people who cited our paper, and I just looked at the top citers, and they all have been extremely active in computing stability of solids. Carlos Vega, Marjolein Dijkstra, Piet Monson, this is also collaborated with Carlos Vega. So there's a whole group of people who either have been using this method or have been using another method and basically comparing with our method. So I wouldn't say that every single one of these used the Einstein crystal method, but they either used it or extended it, or they say what we have is much better. That's or at least equally good. And so I want to say a bit about other methods, but again, in view of there's a limit in time and also a limit in my knowledge. But I want to say a few things that I think are interesting. And I will say a bit about other coupling fields. As you know, the Einstein crystal method uses a harmonic spring to tie the atoms to the lattice size. But there are other fields, and I'll come back to that in a minute, that you can use. The other thing is something that I think was referred to in the questions of the previous of Tony's talk, and that is that in our calculations we fixed the center of mass of the whole crystal. So we had a fixed center of mass Einstein crystal, but actually what Vega and Noya did is they said we fixed just one molecule, and if you fix one molecule, the thing also can't drift, and that again is important to make the thing computationally well behaved. But so this is also a method that works very well. And the other reason I said I'm not going to review everything is that actually there are actually published reviews on the technique that mention many more of the techniques and methods that have been developed since then than I will be able to mention. I just want to say a bit about the other coupling fields. So this is actually a project that was started by Bianca Mladek when she was with me in Cambridge, and it was doing calculations where the Einstein crystal method was not attractive, and the reason why it wasn't attractive is because we were interested in cluster crystals, that is crystals where there could be more than one particle on the lattice side, and that is because these particles were soft and interpenetrable. And then of course tying every particle to its lattice side was not meaningful. And so what Bianca did instead, together with Patrick Charbonneau, is to use as the potential a finite potential where particles could be trapped in wells. And so there could be one particle in the well, but there could also be 2 or 10 or 20. And you just, as you switch on this potential, you basically, you can compute the free energy in the limit of the strong interaction. You can still compute it analytically. So it is a technique. You switch on this interaction, you switch off the interaction between the particles, and again you know the analytical result. So that is a method that worked well. I should also mention that a similar but different technique has been applied by Tanja Schilling and Friederike Schmid to compute the free energy of a liquid. Now you think you don't need it, but actually it's a very nice way of computing the free energy of a disordered structure, as long as you can equilibrate it. And the method is a bit similar in that sense that it also uses an attractive potential, but then the attractive potentials are localized at points of where atoms are in the liquid, and then you slowly switch on the interaction. And then every attractive potential attracts one and only one type of particle, and then you have to do all kinds of tricks to get the correct answer. But in that way, you can compute the free energy of liquids with the accuracy of the Einstein crystal method. And this is something that Tony did not mention, but you'd think, well, the Einstein crystal method is all fine, but is it if you can compute things directly by thermodynamic integration by changing the density, that should be better? And the answer is no. The Einstein crystal method is typically much more accurate than what you get by compression. So this is a rather accurate method to compute free energy of liquids. And a similar, although I must say a bit different technique has been recently used by Berthier and Parisi and others to compute the configurational entropy of polydispersed supercooled liquids. But I would say it requires special care, so I will not go into that. Last point I want to say, and I'll really try to make it short, is the Einstein crystal method. Everything I mentioned now, it was in the context of the Gibbs-Boltzmann statistical mechanics. But interestingly, a technique sometimes can be exported outside of their original field of application. And I got interested in a problem that was posed by Sam Edwards many years ago, in fact in 1989, when he proposed that if you take powders that clearly are not subject to thermal motion, and you can't use Gibbs statistical mechanics, how do you describe them? And he proposed a statistical mechanics of powders where the central quantity in that statistical mechanics was the entropy, the granular entropy. And Sam defined the granular entropy as follows: that the entropy is a well-defined quantity, namely it's the logarithm of the number of ways the grains can be assembled to fill the volume V. So what does that mean? Now, here I have an experiment with grains, actually they're marbles, and they fill a volume V. And to compute the granular entropy, you have to take the log of the number of ways in which you can do that. And that in practice, for any reasonable size system, is not possible. But where we could use the analogy with the Einstein crystal method is the following. That we said if you take particles that are not hard but soft, then the system has many local energy minima, and every energy minimum has a basin of attraction. That means if you start here, then it will go to this minimum. If you start to there, you go to that minimum. And so this, of course, is a very low dimensional sketch, but suppose that you go to a bit higher dimension, then you should expect the landscape. Actually, 2 dimensions is also very low. Landscape with many minima, and every minimum has its own basin of attraction. So wherever you start, you end up in a minimum. And that means that the total high dimensional space, so if you have a 3-dimensional system of n particles, it's a 3n dimensional space, and every minimum is surrounded by its basin of attraction, and together these things completely tile the space. So this volume of the space, and I just use units 1, 0, and 1 now, but the volume of the space is trivial. It is v to the power n. The idea now is that if you can compute the volume of these basins, you can count the number of states. And the idea is really that you say the total volume of the space, this v to the n, is equal to the number of states times the average volume of a single of one of these basins. And once you have omega, you have the entropy. And the key point is that you have then translated a counting problem to a sampling problem. But of course, how do you compute the volume of a basin? Well, that precisely is where the Einstein crystal method comes in, because we just say, let's define the free energy as minus kT times the log of the volume. And then that is what we did in the calculations. And maybe I have even something that moves, I don't know. Yeah, so this is your sample. The boundary says this is the boundary of the volume. If you go somewhere else, you go to another minimum. You sample it, and then you slowly switch on the free spring constant, and you go to the Einstein crystal where you know the answer. And that, as a consequence, meant that we could compute numbers of packings that were actually very high. So this is 10 to the power 250, which is something that you can't do by brute force packing. And that's the power of simulation, that with new algorithms, you can sometimes do things that no increase in computing power could achieve. Okay, now I will stop on a slightly more light-hearted mode, and that is how to become a famous scientist, because of course, much of my work certainly has made use of the Monte Carlo method, and which we know under the name Metropolis Monte Carlo. And so, of course, what does the rest of the world know about Nick Metropolis, who was leading the team that that developed the Monte Carlo method? Well, it's interesting if you go to Wikipedia, because there he is, actually at a younger age, and it says movies, husband and wives. Well, that's curious. And then actually, in fact, if there is a movie, Husband and Wives, and if you look, then you see the cast. Nick Metropolis, TV scientist. Oh, so then you actually go and look, and you can rent it, and then you look at the movie, and here's a movie. And again, I can't, if the sound is not coming through as it seems, then I can only tell you that what he is saying is that he was telling this story about that Einstein said that the good Lord doesn't gamble. But that's why Nick Metropolis ended up becoming famous as a TV scientist. It is something to bear in mind when you're embarking on a career in science, that in the end you become famous for something completely different. Let me stop here. I want to thank, of course, Tony. My students, postdocs, collaborators, colleagues have collaborated with many things. I mean, now that I'm officially retired, I'm a parasitic scientist, so I'm relying more and more on collaborations, and I enjoy it tremendously. I thank Cecam, I thank you, and of course, I know that it's a slightly strange presentation, so you know that wasn't chicken, but of course, even if you have chicken, you never know whether it's chicken or real chicken. And with that, I'd like to thank you.
Okay, thank you very much, Dan, for this presentation. We are running a bit late, but I think it's good to devote a bit of time for a few questions. So again, I remind you to those who are attending that you can pose your questions through the Q&A feature of the Zoom, and then I will relay them to Dan. So actually, the first one is actually 2 questions by Carlos Vega. I think he was quoted during the presentation, so he has the right to also make his point. So there is a first question about your method, And then he says, since the method can now be used in popular MD programs, not just in MC homemade programs, will that provoke an explosion of the method in many areas? Solubility, calculations, for instance, force fields for fluid solid equilibrium?
Yes, the thing is, whether you can do it in MD or well, the main thing is that as the techniques get embedded in widely used program packages, of course it will result in a wider use. There is one thing that I would like to say that the people who do it know, and the people who don't may not have thought about. You have to be extremely careful when you use molecular dynamics to simulate either an Einstein crystal or a crystal that's almost Einstein or almost harmonic, because you can have ergodicity problems. So you have to make sure that in that case, you do the simulations with a good quality, for instance, Boosie style thermostat. So really good quality, so the thermostat, so that you don't get these, you don't get trapped in well, subspaces or phase space.
And he ends with thanking. He says, Dan, Tony, thank you for this very useful method. And sorry. He says that in Madrid with Eduardo, Sal, Pascal, McDowell, we're lucky that you never thought of using it for water. Why?
Carlos knows the answer. Because I mean, in many talks that I've been given, I was talking about argon and about colloids, and I would say, so argon is supposed to be a simple liquid and colloids are complex liquids, although by now I would turn it the other way around. And then you have the third category, and that's water, and I call water a nasty liquid. Water is the most difficult substance on Earth almost, and so I just scared of water.
Okay. So then I move to the next question by Sangiole. Says, great talk. He asked, is there any change that one would need to apply to the Einstein crystal in order to compute the free energy of a finite size structure, assuming there is no degeneracy in the way the components can arrange?
Actually, the method works. I would say it's always applied to finite size systems, and so you can take pretty much whatever target structure you like, as long as it's stable, and the method in principle should work, as will many of the other methods.
Okay.
And of course also if you want to go quantum, so if you use path-integral Monte Carlo, you can do, and actually it has been done. Carlos also knows that, and David Manilov laws.
So Shankanak asked for partition function calculations for solids at high temperature. It becomes very important to decide the integration interval for the integration of the Boltzmann function, which is basically the integration interval over Mahalanobis distance for perfectly harmonic solids. How to decide this interval in a definite way? He said, note that the importance of this interval becomes even more critical for non-harmonic solids.
I try to. I'm not quite sure that I get the key points. Can you say again what was it, where?
I think that the point is decide what is, if there is a systematic way or definite way to identify the right interval of integration for the, he says the Boltzmann function. I understand the temperature range or the range in change. Sorry, not the temperature, the change in lambda. Your case.
Okay, I mean, because if you phrase like that, I mean there are two problems. One problem that you could have is if you go to very small coupling constants, if you don't constrain the center of mass or you don't fix a molecule, then the integrand will diverge in the thermodynamic limit. So that is a bit nasty. You have to do something about that, like fixing the center of mass. And the other limit is if you go to very large value of lambda, then there may also be a problem if you if your real system has a potential that diverges at the origin, and then there's a small integral divergence of the integral that is unpleasant for the numerical approaches. Actually, there's something that Broughton and Gilmer, I think, missed, but that's not very important. But it's also the main thing is that what you should do then is what we have been doing in our recent calculation, but also what Michele Ceriotto and Bing-Xing Cheng have been doing. And that's just the last bit, you use perturbation theory. So you use the perturbation expression, then it's all perfectly well behaved.
Okay. Then the next question is also by somebody who was mentioned in your talk is Henk Lekkerkerker directly.
Yes.
So this is a challenging question. He says that today we have heard about the tremendous progress in crystals, be it spherical, rod-like, plate-like, or molecular, but when we will have a theory of the glass phase?
So this is not a difficult question. This is it is a trap, because I mean, some people will say, "Oh, but there is already a theory of the glass phase, and it's mine." I don't say that, but and so I think that this is a minefield. The thing is that there's certainly, we understand much more about the glass phase than we did many years ago, or not even so many years ago. Let me focus just on the role of simulation in studying the glass phase, and I think that there the recent work of Ludovic Berthier and Patrick Charbonneau, etc., has really made a difference, because they have been able to prepare really stable glasses, and in such a way that these glasses are equilibrated. So these are typically polydisperse glasses, and so they're now able to go down to conditions where they can equilibrate on a time scale that corresponds to experiments that would have been running for a very long time. So it is now simulations start to really get into the regime that you can compare with experiments if you try to understand the nature of glass transition. That's not the same as saying there's a theory. You shouldn't ask me.
Yeah. Okay. Then the next question by Xing Wang. It's about going beyond these Lennard-Jones potentials that you were referring to also. It says, nice talk. Lennard-Jones potential functions can perfectly describe the interaction of argon atoms, but there still lacks a unified potential functions to describe interaction of water. We have to use different potential functions for different research purpose. Does a unified potential function for water exist? I think molecular dynamic simulations is and will be the only useful for simple fluid and solid, but not for the real and complex matters like water.
The last sentence combines two things that I think are not necessarily correct. So no, there is no unified description, and the reason is that life is not simple. There is no free lunch, and so what you see happening instead is that increasingly effective. So first of all, if you have infinite computing power, you just would now use some level of ab initio quantum simulation to try to simulate real substances. In practice, what happens very often, and there's many groups working on it, and I don't have to tell this at the Marvel Symposium, to actually also try to use machine learning to extract effective cheap force fields from many body potentials. And that's pretty much as good as it gets. I mean, so with those cheap force fields, you can then start predicting phase diagrams. And again, people like Binjin Cheng and Alex Reinhardt have done a lot in this direction, but also other people do. But in particular in the context of computing the free energy of solids, I think Binjin and Alex have done a lot. So you take the best possible description, you use machine learning to get an effective force field that works well and that is not too expensive. And that's it. I mean, so it doesn't mean that molecular dynamics cannot be used. Molecular dynamics is fine. Okay.
Thank you very much. So I think it's a good moment to stop this part of the two presentations. Thank you for this, both Dan and Tony, for these insightful lectures and the associated discussions. And then we move to this, the last part of today's event, the one that is a bit less orthodox, but I think it will also be lively and insightful in different ways. And you can, all participants, still participate using the same feature channel through the Q&A to put your questions. And now I pass the word to Cecam Deputy Director, Sarah Bonella, who will be chairing this part of the event. Sarah.
Thank you very much, Ignacio. And well, let me start by thanking Dan and Tony, because I think that this was a super afternoon of science so far. Now, as Ignacio said, we are now moving to a slightly unorthodox part of our meeting, but this is very much, I think, in keeping with the spirit of Cecam has been described by our two speakers, and that I think we try to maintain as much as possible in this strange modern world in which we live. And so this is where we go beyond, you know, the equations, the algorithms, and so on and so forth, to understand a little bit more about the atmosphere and what does it mean to be part of the development of an exciting new field. Now, we've heard Tony tell us that he's not old enough to remember things that Kepler said. Dan was strangely competent about that, but we're not going to make assumptions.
I hear voices.
Exactly in the evening, right? But the
usually
purpose
Clausius though, but okay.
It's true, actually. He often calls you on the phone, if I remember correctly.
Absolutely true, yes.
But now, so this is where we're going to mix a little bit of history, a little bit of behind-the-scene anecdotes and personal stories, I hope also from our two speakers. Now, to underline the informal character of this part of our session, I will sort of steal something that Nicola did the last time, and I think we should probably drop these beautiful but rather formal-looking backgrounds that we have with logos and names of funding agencies, just because it feels more relaxed. So I don't know, Ignacio and Nicola, if you want to do it, but I feel I should do it. As Ignacio said, participants are more than welcome to ask questions. They can be technical questions, but this is also the time to go beyond that. We've done this a little bit, talking about the kind of computers and computer programming methods that we had at the time of the 1983 Cecam workshop. I have to say that being deputy director of Cecam is something that really makes you feel how strong the connections within a community can be and how important that is for the development of new ideas. So, I mean, I trust Tony and Dan enough to know that they will not go down memory lane in a nostalgic, oh, that was the Klondike good old times, and so on and so forth. But I would love to start this conversation by asking them to compare a little bit or to isolate the elements that they feel were critical or most exciting at that time in their way of doing science at that time, and see how they have sort of evolved to where we are now. I mean, both the good and the bad.
Who should start?
Let's pick Tony, because you've just finished.
That's right. That's a good idea. You see, I changed my background.
I did.
Everybody shows their bookcase, so I thought I use an iPad.
Okay, so I guess, so what's different? I think the thing that strikes me most is the lack of space for young people to create new things. I mean, the fact that they do anyway is even more remarkable. But, you know, when I compare my experience when I went to Lawrence Livermore with the experience of young faculty in our department, you know, at Livermore, I basically had my work and that was it. Anything other than my actual research could be done basically one Friday afternoon a month, and maybe not even that. And that's such a different experience for young people today, spending enormous amounts of time in meetings, writing proposals, managing grants, managing students. It was basically sort of like an extended postdoc at much better salary. So that is something that I think is, the problem is I think that tends to press faculty towards picking the lowest hanging fruit, because, you know, if you take 10 years to solve a problem, you'll be on the breadline before you're halfway through. So I think that's something that, for the good of science, actually needs to be addressed. I think it's probably more true in American academia than it is in Europe, but I can see that the same thing is still spreading, and the relentless pressure and demand for papers. So that I think that would be the biggest single change that I would notice. And I guess, of course, the increase in resources. I mean, that's, so, you know, commenting on my paper with Les, I would just say in defense that one of the ongoing questions in high energy physics at Cambridge at that point was, who is AL10? Because AL10 was my user ID, and high energy physics was used to dominating the computer time on Cambridge's one IBM computer. So the whole university, the UK's elite science school, had one computer with about a 5 megaflop speed, usually dominated by high energy physics. But what I'd done, I had all of those simulations stacked up back to back with elaborate fail-safe mechanisms built in, so I could just desert it. And then I took my girlfriend on a holiday and left several thousand jobs in the queue. And when I got back, there was that was the question that I had to address. What had I been doing? And I think that was those not so great simulations of the three-phase coexistence. But
Dan?
Yeah. Well, I mean, first, what Tony says about the push to get people, I mean, to not just produce papers, but I mean, it's very often it is even more mundane. It's getting grant money in, which is, I mean, it is mysterious why publicly funded universities should then try to get their money once again by getting grant money, or now they have to, because the funding has been cut so much that without that money they couldn't survive. But it is very depressing, because indeed, if you look at new developments, they take a decade. I mean, maybe sometimes if you're very, very lucky, or if you work like on a vaccine this year, you can get things to work very quickly. But don't get it wrong. All these rapid developments during the past year were based on years and years of underlying research. And so if people can no longer take the risk to do that, then you're undermining the whole sort of the reason of existence of universities. Now, I should also say that for me, what was wonderful working at Cecam and working in computer simulations in the 1970s already, is that it was not an accepted field. So I mean, I did simulations when I was a postdoc at UCLA, and there my supervisor, and actually the environment was very supportive. But in the Netherlands, on the whole, I mean, there was a huge debate about whether computer simulation whether it was theory or experiment, and the theoreticians said correctly it's not theory, and then the experimentalists said completely correctly, oh, it's not experiment either. And so basically the result was that as long as you didn't ask for anything, they left you alone, and that was wonderful. So that's no, I mean, being in a new field, or if that was not so new, but certainly it was growing rapidly, is a fantastic experience. And I mean, and when you see the same thing happening, that people, of course, as new things emerge, people jump on it, not just because it's a fashion, but also because in a new field you can do things that are really important and transform what's going to happen.
Mm-hmm. So I guess that must have been exciting, right? I mean, being part of something that was emergent, controversial, but where progress was somewhat palpable.
Absolutely. But I mean, I would say that in particular at that time from the theoretical physics community, there was a lot of reservation against computer simulation. And even, I mean, like the older Wainwright simulations of hard sphere melting, there were very respected physicists whom I won't name, who just said it can't be right because, and then there was some argument that we now know, or even then knew, was not right. But yeah, that's also nice that you're in a field, you hear criticism by famous people, you think, no, you don't have it right.
Right. So do you have advice for young people who are now under these pressures that you have described to, find ways? Should they just become hermits and then go to mountains and forget about meetings? Or
I don't know. I mean, first of all, precisely, and Tony probably will say the same, precisely because we started our career in such a very different situation, we are probably the last people to give advice. And so I don't know. I can say one thing about advice, and that is that at that time I got advice about what I should do with my career 3 times, and every single time I ignored it, and I never regretted it. Of course, what it always meant is also that you then go for the high risk route. So the first person who gave me advice was Bernie Older, who unfortunately passed away in September. Because I was working on a project that actually had to do with what I was then doing at Cecam, and Bernie said, well, actually, that's not so interesting. I mean, that's typically Bernie. And so he said, well, you know what? I've looked at the velocity correlation functions of hard spheres, and for short times, we've done the N-square approach. We understand it completely. For long times, we have the long time tails, and we understand that completely. The intermediate regime hasn't been studied so well. And I thought, and I'm not going to do it. I mean, okay, so anyway, ignoring advice is very useful. But you sometimes...
Yeah, I should mention that Bernie got me to do that some years later. So he was clearly smarter than I was, because they were very long calculations and they never proved anything particular. So that showed very good judgment. Yeah. I guess I would think the same thing. You know, it's very hard to advise because, you know, I've seen some of my colleagues miss out on opportunities to lead in their fields, perhaps because they took a different route because they couldn't get their novel idea funded, and so they changed and looked for something safer, which I think is really, that sort of thing is really unfortunate. But at the same time, it would be very hard to advise a young faculty to take a potentially career-ending risk. So I think in many ways perhaps the onus is on the more senior faculty that has get into positions of influence and maybe administrative power to do all that they can to push back against those kind of pressures. But other than that, it's just, you know, and maybe science itself will evolve. I mean, science today is I think much more collaborative in the sense of large numbers of contributors. I mean, from the sort of era of the 1980s and particularly before and maybe a bit afterwards, most papers were one or two authors. And now I think a one or two author paper is maybe getting to be more and more of an exception. So perhaps there's also a way in which science itself is adapting.
Yeah, I think we have a question that sort of builds on your last comment, which was, you know, how can we think about improving the situation around grants, right? Because it seems that everybody agrees on the fact that they are problematic for the reasons that you say, but then there is no easy solution, right, to improve the mechanism. So I guess this is part of what you're saying.
Maybe I can say one thing about that in the context of European grants. Of course, the UK has, in its infinite wisdom, decided to leave the EU, but at least in principle, they're still part of the European Research Program. The thing that is actually very useful if you want to do research that is not too strongly bound to milestones, deliverables, all this kind of stuff, is the European training networks, because basically the EU cares about the training aspect. And so if you write a proposal, I don't know whether it's still completely true, but it used to be that only 15% of your points are for the science. And of course, we scientists tend to think that our science is the most important, but that's not what the way the EU thinks about it. But it also means that if you then do a project, you have a huge amount of freedom to redefine what you're doing. So there are certain kind of projects that run a lower risk. Of course, with these EU things, you have to find partners, but that we all like anyway.
Right, thank you. Ignacio, Nicola, of course, feel free to step in if you have comments or questions that you would like to ask. Going a little bit back then, I mean, because we've established that simulations were not as established as they are today and so on and so forth. So how did you first think that this was something fun, that's what you wanted to do?
So for me, I mean, I'd never heard of the idea of computer simulation. So I was trying to do, what I was actually thinking about was trying to calculate solubilities of ions. And I was thinking about, so I was trying to do, knowing nothing, I sort of started to develop a version of thermodynamic perturbation theory. And one of the demonstrators, Paul Madden, said, oh, you need to go look at this paper by Barker and Henderson. So when I looked at the paper by Barker and Henderson, I found that they developed that idea in far more detail than I had. But it still looked pretty formidable. And then Paul told me about molecular dynamics, which sounded really, I mean, so theoretical chemistry at Cambridge at that point was almost all quantum chemistry of various kinds. And that sort of thing never even occurred to me. But they told me to go talk to this guy, Les Woodcock, who I believe was the only person in Cambridge chemistry, at least at that point, was doing any kind of computer simulation. And we never did solubility. I did try to simulate water because I realized the solubility was too big a problem. So I needed to do a simpler one. I thought I tried to do water. But I ran into all kinds of technical difficulties associated with summing the long-range forces, and failing to solve that problem was a big chunk of my PhD. So. But yeah, so it was not an intentional thing, really. It just happened.
Yeah, in my case, and after my bachelor's degree, I started actually as an experimentalist in physical chemistry for my master's, and we had group meetings where we typically would every week come together to work through an article, and my latest thesis supervisor, Jan van Elske, he said when I came, well, we are interested in spectroscopy, and in particular, so we think about how these dipoles rotate in the liquid. And I thought, dipoles rotate in the liquid. Come on, it's quantum mechanics, it's levels, etc. And then I read articles by Zwanzig and other people on linear response theory, and that completely changed my world, because suddenly you realized with classical simulations, so with classical pictures, you could understand a lot of what was going on in spectroscopy, where people normally always were saying, oh, there's this level and that level. And then what really got me much more familiar with simulation is a review article by Bruce Byrne and Harp. That was a really nice overview of more or less the state of the art in the early 70s. And then the other thing actually is that at some point when the first simulation I ever did was when Les Woodcock was visiting, and he gave a talk about simulations, and he explained how a program worked, and he said it is so simple, you can more or less write it over lunch, and everybody was laughing. And Les and I sat down over lunch and we wrote the program, and it was running in the afternoon. So that's the other thing. A basic program is incredibly simple, so you can get started really well. And so it's this combination of really being able to directly ask the questions to a system that you want to ask, because I was doing spectroscopy, and you could only ask those questions that could be answered by spectroscopy. Many things couldn't. In simulation, you just decide what you want to know, and that I thought was really, really liberating.
It's a bit like falling in love. Huh? So the first time you see something that then grabs you, and so yeah. But this is interesting also to me now, because today this notion that a young student or someone who starts doing simulations goes through the process of actually writing his or her first code. This is a lot less common now, right? Because we benefit from the existence of large packages that solve the problems and so on and so forth. But then one has to ask the question, how much are you missing? Because you're not writing line by line what you want to discover. And so that's maybe also something else that we should think about, no? when we give simple problems to our young students.
Actually, maybe in this context, I mean, as you know, together with Bernd Smith, we wrote a book on simulations, and the first edition was really sort of aimed at people who would be writing their own code. And now we're working on the third edition, and basically the thing is that, as you say, most people use program packages, and they should, because you don't want to program your own protein simulation or anything like that. But you have to know what's inside, and so understanding what you do is become even more important.
Mm-hmm. That then misses this, as you said, this immediacy of jumping into a code and understanding how it works. No? It's really like a higher level understanding.
It's true, but I mean, but every bit of the code, I mean, I mean, if you bring it down, like the core of a molecular dynamics program is only 10 lines or so. I mean, so in that sense, there's always bits that you can always program. A Monte Carlo program, again, a few lines. So there's certain things you can do yourself, and certain things where you absolutely don't want to do it yourself. Like, you know, you're not going to write a graphics interface or anything like that.
Mhm.
I mean, in the past we did. It was awful.
Yeah, there is progress. Yeah.
I think that is an important. I mean, the amount of time that I've spent in my career writing extraordinarily boring programs to take the output of a simulation and turn it into something that could be plotted, something that could be analyzed in any sense, was just enormous, because every one of them, every calculation we did would generate several programs like that, all pretty much the same, all equally boring, but all taking a non-trivial amount of time to code and develop. And the modern infrastructure, especially with MATLAB and Python, has really made this just hugely better. And I have to say, now I'm using a lot of not molecular simulation software, but CFD simulation software. And the level of quality of the software development is sometimes just absolutely extraordinary. It's nothing I could remotely have done. And that they've solved so many things that I recognized as problems when I was writing programs that other people might want to use. That problems that I never could figure out, and there are solutions that people have come up with to make these general packages accessible and useful. And I just think that those are extraordinary efforts.
That's absolutely. I mean, I think we should recognize that, again, Nicola is here, and there are projects like Marvel that do insist on this notion that there is a software infrastructure that should be recognized as, at the same level of importance as experimental infrastructure or hardware infrastructures are recognized at the moment. And then
absolutely, so. and also, I mean, certainly maybe it's now less, but I think that in the past, people who did simulations, developed new techniques, sometimes thought that they could also write software. But I mean, I can't. I mean, I can write a program that runs, but I would not want to dump that on anybody. It would be terrible. I mean, so you have to know your own limitations.
Mm-hmm.
And recognize professional profiles.
Yes, and that's right, exactly.
And give them recognition and provide paths for those.
Yeah.
So if nobody asks questions, I'll just keep chatting and enjoying my time here. So be aware of that for a few more minutes at least. I wanted to go back to this mythical 1983 Cecam workshop and ask you, well, first of all, MC in an MD, not an outlier. How did that happen?
Well, I think it came because of this. I mean, so the parallelogramon was written in an MD context, so that was part of the workshop, and it came out of the discussion of that work. At least that's my recollection, and basically saying, well, what are the alternatives? I mean, if we don't do parallelogramon, what do we do about looking at phase coexistence? And the obvious thing was free energies. So that's really out of that. I mean, I think we left that roundtable discussion with the idea that we were going to try this Einstein crystal at the workshop and just see if it worked. I mean, I remember that we had, I think our major concern was just the number of integration points that it would take to integrate the potential. And my first guess would be something of order 100, which would have been next to impossible. But the combination of the transformation, especially the Gaussian quadrature, which I didn't know about, Dan knew about the Gaussian quadrature, made a huge difference.
so we have a question that takes us back to the differences between, pressures today and pressures a while ago. I will ask that question, but I ask Amit for a few minutes of patience, because I was curious about, there is something that Dan has mentioned and that he always mentions when he talks about this method, and it's how much he enjoys the fact that you guys were at a workshop that was supposed to focus on a set of topics, and instead you went off and did something essentially unrelated, the odd one out in your talk. And I just wanted to ask you a bit more about how important you feel that having the possibility of doing this is, together with this other aspect of being in a place where you can go off and do your own work, but then there are these roundtables where you go and share ideas and possibly.
It was so important that we actually had a follow-up workshop on free energy methods. that we spent that workshop developing lattice gas automata for suspension. So the Cecam provided a structure that gets things started, but I think it's an excellent creative thing, because Cecam never tried to control what people did. I think that was crucial. There was no this is the focus of the workshop. You really should be working on this problem or that problem. It was, this is the focus of the workshop. Let's discuss and then just see where it goes. And I think that is a good example of scientific leadership.
It's like a jazz band, put together a group of very good musicians and see what comes out. Dan, would you like to add anything?
No. I think that was absolutely essential. That you followed the ideas where they went. Just to add something about why Monte Carlo in a molecular dynamics context. I should say first that actually before the workshop, I was working on liquid crystal models. They were not looking at freezing, but phase transition, and that they were all far easier to implement in Monte Carlo, because these were non-spherical particles, and I've also done simulations of the dynamics of hard non-spherical particles, and that is, at the very least, it's always approximate, and there are now much better techniques, but at that time it was hell. So I thought, I was not going to do it. And as I had these non-spherical particles for phase diagrams in mind, and I was thinking in Monte Carlo terms. And of course, my good friend Giovanni Cicotti did have a very high opinion of Monte Carlo, although at some point he sort of, I would say, has accepted that it was also a role to play. But that was also nice, because it meant that we could do our work undisturbed. I don't know whether Giovanni wants to respond.
Well, that's a mistake, Dan.
Well, he can't speak. Just
okay. So
no, but then I have to read what he writes, right? And you used stars.
But you could say whatever you want, because it'll all be asterisks, right?
Exactly. And beeps. That's true. Okay, so let me go to Amit's question now. So excellent talks. Thanks a lot. For young researchers, it's not only pressure to get the grants, but there is also a lot of stress to publish in high impact journals. And over the years, the quality of papers in prestigious journals has dramatically gone down, and the collaboration with the right set of researchers tends to take you to that path. So I don't know if it's a question or a statement or something we should all think about and commiserate about together. But
okay, but I think it's true. It is awful. It's true. And I would say basically repeat what Tony has said, namely that the onus is really on the academic community. Because, for instance, if people apply for a job and you say how many nature science, nature, physics, material, etc., rather than looking at the papers, then you reward this. It's not that there's anything wrong with having papers in high impact journals, but what you really, what I think you should do is if somebody applies for a position, is to just ask them just mention 1, 2, maybe 3 papers of which you're really, really proud. You really think this is what I have done and that I'm proud of. And then I think these panels should be reading those papers, so that you look at the science and not, I mean, after all, it's the papers that make the journal. It's not the journal that makes the papers, although it's, at the moment it looks that way.
Mm-hmm. Yeah.
Very, very true.
So, yeah, I mean, it's, I find it, I mean, I have never had one of those high impact publications. I mean, PRL is the most high impact journal that I've published papers in, but what I notice is that none of the papers I published in PRL are among my most highly cited.
Yeah.
In fact, one of my most highly cited papers is in the Journal of Statistical Physics, which has an impact factor of about 1. And so, you know, it may not happen quickly, but over the long run, I think it's the paper itself that matters far more than what journal it appears in. Just what I'll give you one recollection I have. I was on the editorial board for PhysRev, and one of the professional editorial staff was proposing that we returned more papers without review. And he does this very quickly, and then he says, way too soon, does anybody object? And over in the corner, Gunther Ahlers growls in his German accent, I object. And then the guy says, the guy makes matters worse. He says, but all the best journals do this. And Ahlers goes, what journals? And then he says, well, Nature and Science. He goes, those aren't journals, they're news magazines. And that was the end. That was the end of that discussion. I mean, Ahlers just killed it, you know, in about 2 minutes. But I mean, that was, but you know, that there was already that pressure, even in like a society publication, and Physical Review still does return a number of, I would say, papers without review, without, you know, necessarily serious consideration, just because it looks too difficult. It's the formulas are too complicated. Nobody wants to review it. It's a problem.
No, I mean, you should also, I mean, take into account that in particular the high impact journals, they suffer from the fact that everybody wants to publish there, so they get completely inundated with submissions, and if they would send everything to referees, and referees already are heavily overloaded, it would also not work. So it basically is a damned if you do, damned if you don't situation.
I mean, I don't think it's the problem with the journal. I think, just as you were saying, it's the problem with the way that those publications are weighed.
Absolutely, yeah.
As opposed to other publications, and the huge weight that in jobs and funding is being given to them. That's where all their power is coming from, and that's really something that's within the community's control. So I mean, this is something that we could fix.
So I think we could sort of pause or end this discussion with this comment from Randall Kamien, who reminds us of the old Soviet saying, there is no nature in science and no science in nature.
Thank you, Randy.
Yes, because. So then we have a question comment by Andrei Zvelinovsky here, who says, thinking about these long special workshops of the 80s, what can be advised to Cecam or other organizations for today's support and training of modern scientists? I will take the question and allow a fully free answer, but first let me state with some pride that at Cecam, we welcome proposals for what we call alternative format workshops that can be as crazy as you want, and as long as you convince us that the science and the training are excellent, we will fund them. Huh? Even today, in these very strange and dangerous times, we manage to fund workshops that last up to 3 weeks. So be aware that you can come to us with those crazy ideas, but please go on and see what you have to say about it.
The one thing you can't turn back is the degree of interconnectedness. So, I mean, one of the things really in the workshops of the 70s and 80s is that people were there and they were not in contact with, I mean, the administrative things at home, all these things. It was gone. I mean, and so you can't pretend that you can eliminate that. Certainly, I mean, certainly the past year we have been on Zoom, Skype, Teams, whatever, all the time. So we are more connected rather than less connected, even though we're all sitting at home or, or something like that. So but I do think that it is really important that I mean, there are, of course, listen, there are workshops that try to follow, or that basically do the old Cecam format, namely at the Santa Barbara, the KITP. And of course, KITP was organized that way because, well, Walter Kohn had seen Cecam and he wanted to copy the Cecam model, the old Cecam model, and somehow that model survives much more there than it does here. So, and of course, there people do have internet and everything, and many people don't stay for the whole duration of a workshop. But still, it is a compromise that at least what you see there, and that is something that I think in Cecam we discussed several times also, is the idea that you have a certain longer themed workshop where not everybody is there all the time, but some people are there all the time, and other people come and go. And it's a loosely bound theme, and then hopefully people will start doing something else. That's
yeah, no. And the other thing, I mean, that I have seen happening in these long workshops is that you typically get a core of younger people who get to stay there for the whole time and work together and go off and you know, form friendships and start collaborations that sometimes last for many years after the workshop. And then you have more senior people that come and go, and that doesn't matter because they come, they contribute, but still you have this presence that provides sort of the foundations of the work done at the workshop. And I think this is something of value that shouldn't be lost.
Of course, Cecam, and certainly in the 1970s, the people who were there were all young. I mean, I was even younger, so I thought they were fairly senior, but Giovanni Cicotti was 32. I mean, so.
Yes, absolutely. So we have a question from Marco Fornari. In 1999, Ginsburg selected 30 important and interesting problems for the 21st century. In your view, what are the important and interesting problems that these fields should challenge?
I don't know. I mean, the thing is that I'm always very reluctant. I mean, I think that people at a more advanced stage in their career should not say too much about the future because it tends to be a linear extrapolation of the past. And so we're probably least capable of identifying the trends, and we probably miss the things that are really important at the moment. That's I don't know whether Tony, whether you would agree or disagree with that.
I agree in general, but I would also add that since I haven't been in this field for I guess close to 30 years, except peripherally, that I would have very little idea. So but yeah, I don't think this idea that, you know, senior people have some sort of special wisdom to offer on such topics, I think is a bit
yeah, no, I mean, let's be brutal. We can quote Planck. Planck
Yeah, exactly.
said science progresses funeral by funeral.
Yes, yeah.
So there was a question by Carlos Vega that Tony sort of answered by typing, but I think it's perhaps going to be fun also for the audio audience. So basically, the question was, how come Bernie Older never got a Nobel Prize?
Yeah, so the answer, I don't know whether Dan would agree, but the answer that I put is that I think in that sort of era, I don't know when it began to shift, maybe 80s and maybe 90s, was that MD was not something intellectually serious.
Yeah.
And that was connected to the fact that technically it was extremely easy to make a program. And so people did not see this as something deep or something, you know, worthy of such a recognition. You know, and I think missing the magnitude of the contribution it made. I mean, I think Dan would agree, you know, in the statistical physics community, I just remember it being regarded as not very serious. I mean, at Cambridge, I would say the attitude was that it was not a fit subject for a gentleman, and therefore ideally suited to somebody like me. So,
No, I think that it's true, and the thing is that Bernie Older's, well, first of all, if you look at Giovanni Cicotti and Battimelli, they have written this book about the history of simulation, and there you see that the impact of computer simulation, just the number of citations of, say, molecular dynamics compared to pretty much all the other things that we consider to be important developments in the physical sciences of the past decades, it beats most of them hands down. So the impact is absolutely huge, but there's two kind of Nobel Prizes that Bernie Older could have qualified for. One is physics, which would have been the natural one, but for the reasons that Tony mentioned, the conventional or the statistical physics community has great reservations about the value of simulation. They thought it was just, I mean, if you're not smart enough to do theory, then you do simulation. They thought it was all about the numbers. Whereas Bernie showed that computer experiments give you insight and allow you to discover new phenomena, which is like what the long time tail study did. But anyway, so they never put him forward. I mean, even the Boltzmann medal, he got very, very late. And in chemistry, where they would be more inclined to reward somebody for a lifetime achievement and for different topics. But physics has to be one thing, so it would have to be long time tails or something like that, or the Hartree freezing. In chemistry, it can be a more long-term sort of life achievement, but the chemistry attitude is, well, wait a minute, his contributions were in physics, and so. I mean, it's not that they denied his importance, but at least the people that I spoke to thought that it was a missed opportunity for the physics community, which probably it was.
I think I remember a comment by Walter Kohn at some point who was saying something like, being a physicist or being a chemist and getting the Nobel Prize in the opposite field and finding itself as a pilgrim in the land of the infidels and so on and so forth. So yes, this certainly played a big role. I'm going to skip to a question or a comment by Rohit Goswami, who sort of ties into what you were saying about the fact that writing code is perceived as an easy thing. And then he was commenting, isn't that still the case? Because programming innovation seems to be rather trivialized unless it comes from another field like machine learning. No comment there in the simulation community. So is this changing in our community? I mean, the relevance of producing good software, I think we have touched upon it in terms of the infrastructures and so on and so forth. So I don't know if you want to add comments to that or not.
Well, I mean, I think that there's two different things. There's one is the good software, I mean, which is incredibly important and is important, I mean, simply to make sure that knowledge doesn't get lost, get embedded in program packages. That's incredibly important. I don't think it receives much recognition as such, certainly not from the community who benefit from it. Mm-hmm. The other thing is innovation. So people who come up with new techniques, that is maybe a bit different, but then I would also say that I think that if you have a new algorithm or something that really makes a difference, I mean, and it's not part of a program package. So if you don't take care of this, then very often it just disappears and is reinvented many times, mm-hmm. Or not. But I mean,
yeah.
I mean, the standardized software, I mean, has had an enormous effect, I think, on ensuring continuity. I mean, so for many years, up till about 2012, 2013, I was basically writing all my own software, and all my postdocs were. But when the postdoc left, the program that he left was more or less useless. It will be, tens of thousands of lines long, impossible for anybody but him to work with. So there was no continuity. But working with actual, open source software, which is not an easy thing. It's all heavy C++, but we've had continuity from postdocs to PhD students, and it's been much more much more productive. And I think the same thing is true on a massive scale in molecular dynamics. So, you know, I left MD when those packages were, you know, first being developed, I think, or first coming to the fore. But
yeah, I think another thing that I find interesting from my privileged point of observation is how different, I mean, I would argue that, you know, people in the solid state or electronic structure community have had a different, or if you want, earlier relationship with the writing of community codes compared to the soft matter and StatMac. And you really see this difference in the way the communities evolve, they nucleate around things, and knowledge and techniques are preserved and passed on from one generation to the other. Now, we have a few more questions, and I would like to take them. I mean, we are running a bit late, but I think we can go on for a few more minutes. There are a couple of comments, and these I will just report because they build on this discussion about powerful aspects of today's way of doing science. And one is from Ali and Elena, who comments on funding and the fact that at a success rate of grants of 10 to 20%, you also have this to factor in, and this generates fake competition to get those grants in some way. Then there was, something from Tony. This was for you. This was, I think maybe we can leave to a private discussion between you and Alexander Wagner. There was, I thought, an interesting question by Ulf Schiller that says, well, many thanks for the brilliant talks and the comments. Both talks have illustrated the importance of computational thinking in driving methods and algorithms forward. What is your view on how past and current developments change the way we should teach computational science to students today?
Hey, Ulf, just saying hello. But yeah, I mean, we're engaged in such a discussion right now in our college about, you know, how to incorporate AI into our engineering curriculum. That a lot of that's driven by the fact that one of the founders of NVIDIA was a UF graduate, and they've donated some enormous NVIDIA supercomputer to the university. And so there's a lot of money going into developing AI now. But, you know, I think clearly our students need to learn to program. I mean, even in engineering, that's typically been at the undergraduate level, something that was very lightly touched on, at least at our school. So the students have for years had a single class which is supposed to teach them how to program and teach them numerical methods, and it's really unsatisfactory. But I think the college is going to move towards a gen ed class teaching the students to program, and then the different departments can sort of fan out from that. But I think it is, you know, there's a difference I can see in the postdocs who've worked with me, like Ulf and Vitaly Stachenko, who also came from the espresso world, that have had serious training in computational science. They can write much better programs than people that just sort of picked it up, you know, just to solve a problem like Dan and I did.
Yeah.
So I think, yeah, this is something that where you fit it in. This is a huge constraint. So when I went to Florida, a chemical engineering degree was like 172 credits, and now I think it's 131, and it's moving to 126. So you know you've lost almost a third of the degree program, and so then it becomes really hard to fit new things in. But
yeah, I mean, there's maybe one thing that is useful to point out, and that is the role of I think it's very important that if you want to understand techniques, that you can also program them in a simple form. Now, one thing is, of course, which language. And this was an issue when I was a student, and it's been an issue ever since, because there was always, whatever language you used, the computer scientists were always saying, yeah, that's outdated, etc. So I've been told to use Argon, I've been using Pascal, all this, the whole stuff, everything, and they come and they go. I mean, there's a Bob Dylan sentence saying, I forgot more than you'll ever know about her. I mean, I forgot more languages than than I absolutely can remember. And so the thing is, languages as such, I mean, it is clear that people must know a language, but for the rest, as long as it's a flexible language, and I think Python at the moment is the default option, as something that's flexible, simple, it gets you off the ground quickly, and don't believe necessarily that it will be there forever. So don't invest your whole. I mean, I've together with Mike Allen at some point we written an article about dynamics of hard Sphero Cylinders, liquid crystalline molecules, and it was written giving code for a particular supercomputer, namely the CDC, whatever, I forget what it was, that had very special instructions, which he gave the instruction. I think 2 years later, nobody could understand anymore what was there, because of course that had all gone. And so languages come and go. Well, I mean, except for Fortran, there's a, well, C++ is now similar, but I think somebody said about Fortran, I don't know what the computing language for the future will be like, but I know what it's going to be called. It's going to be called Fortran. And so basically Fortran typically takes in many of the development, but there are a few languages that now have shown that they're fairly long-lived and as long like, and I think that Fortran, C and Python are typical languages that you can use, but then don't overestimate the importance of a language and say, oh, this is the language you should use and that is the language you shouldn't use. You shouldn't use BASIC if that still exists, but okay.
But I think, yes, I agree. And then, I mean, you know, nowadays with all this new infrastructure provided by things like Jupyter notebooks or environment, exactly. These kind of things, I think it's always important to separate the technical language that you're using with the ability to develop what I think can be called algorithmic thinking, no? So the way in which you would go about writing a code.
Yeah, and the thing is that also that the languages that are relatively simple are by now also reasonably fast. So that is not so much a problem. I mean, of course, if you want to do production runs where, I mean, a factor of 2 makes the difference, then maybe you would do something else. But otherwise, forget it. I mean, it's just.
Yeah. But then this would probably open a much broader, and we don't have the time for discussion, which is also, you know, how do you use simulations and modeling while you're teaching physics or chemistry or engineering at an undergrad or at a graduate level, no? Because this is another, you can do a lot of statistical mechanics in using computers and simulations nowadays. Now, we have 3 more questions / comments. I am going to go through them, but let's maybe be fast, and then maybe we can move towards the end of this lovely afternoon, I have to say. So there is, so I wouldn't want to see this ending, but I guess at some point we'll have to say goodbye. But so from Fabienne, probably a belated comment, but recently some research in machine learning works at predicting the impact of published research, and then he gives a reference to a Nature paper. Any opinion on whether this is a good thing for scientific practice if adopted by journals? So
I would say, you know, especially if that article promoting it has been published in Nature, it's an absolutely terrible idea. But probably one that will be unduly influential.
I think that if the answer is it good for the journals, those journals, the answer is yes. But for the rest of us, no. But I mean, after all, we are in a sense neural networks. Many people know exactly what you have to put in and how to say it. So people are already doing it. Mm-hmm. And some people are good at it.
And then we have a question from Joshua Gramlich, and I think it would be perhaps also interesting to put this in the context of a broader answer from Ignacio and Nicola, because this also touches upon what we are doing and what we should be doing in the future. So this is a lovely experience being here today. Thank you very much. I know I am enjoying it immensely. I am wondering if in the post-pandemic world, discussions like this will become more common. I hope so, very accessible and enjoyable. Yeah. So Marvel and Cecam leaders.
Yeah, I mean, I think that's there's the motto, no, that with the crisis there are new opportunities, and certainly we have learned about how to keep this communication ongoing during the last year and a half. And indeed, I mean, there is value to operating like this. I mean, we had a number of email exchanges with Dan and Tony, whether we were going to have the meeting online or wait to see if the situation was improving. And And finally, after some delays, we decided to do it remotely. We certainly are missing part of the direct contact, but I do think that that this is an opportunity to also welcome participants and make participants active that wouldn't be able to attend otherwise. So I'm definitely, that's something that will be sustained one way or another. And just to give you an example here in Cecam during this year, we have upgraded the room downstairs so that we can facilitate the active participation of remote people together with those who will be attending. So I think this is something to be explored. I think it's important also to find the right balance. We had the experience and the example of this 1983 workshop, the importance of having people interact freely, and being at the distance, that's difficult. But for events like this one, I think that there is definitely value, and that's something we'll see developing, yeah, for sure.
Yeah, I think this is a really nice thing, because we are a much larger group than we could be if we were all meeting in one place. And so to have something like this be part of a Cecam workshop, I think could be really nice, because the workshop could both feed into the sort of Zoom session by generating some ideas, and the responses from the Zoom session could perhaps feed back into the workshop, and things following up after that. So I think it would be a really good thing, and some benefit from the pandemic at least.
Yeah.
I think if I can interject, this is a brilliant and wonderful suggestion. That is, I think, there is a great need from a broader community to be able to engage. And traveling is a privilege, it's costly, and it's polluting. So thinking that, more often, maybe even in the context of Cecam workshop, there is a dedicated session that engages with the community that couldn't participate, would be great. And in this also, being a fan of Car Talk, I don't know if Tony in the US listens.
Oh yeah, we used to listen to
Car Talk. There is a, Stump the Champs. There is also, the moment in which the audience really asks the expert the very difficult questions. And so, it's also, a service that one could give to the community to be able to, engage some of the, visionary and experts.
Absolutely. So question from Vladimir Lobaski. The materials modeling community is actively discussing combining physics-based and data-driven methods, which is now becoming pretty common. Should the computational physics students be trained in machine learning and advanced statistics as well? And then chapters about that included in the next Frankel and Smith edition.
Or for the fourth one, yeah.
No. I mean, the thing is that clearly machine learning, or however you want to call it, is an absolutely essential ingredient of science. I mean, the thing is basically with machine learning, you can't improve the power of a technology by a factor 10 to the 18 and assume that it will not affect everything. And that's what happened with computers. So at the moment, there are so many areas in science where machine learning is, I mean, if you talk about just machine learning as a tool to quickly recognize patterns, like does this patient have a pneumonia or not, that is not the kind of machine learning that you would like to see in science. It's just data analysis, correlation, and sort of without understanding what's happening. But there are many areas of machine learning, of aspects of machine learning that are very deep and give you insight. And so the question is really, what do you include and what don't you? I think that people have to be familiar with the basic concept very much. To what extent in a book on computer simulation, like simulation techniques, you should include it? Well, clearly to some extent, but then again, it is a huge field, rapidly growing, so you have to limit yourself to what you address, and then hope the same as with in the earlier editions, which we maintain, we consciously did not discuss quantum simulations, and the idea was really let the real experts write on that. And so there will be something similar with machine learning, and when we talk about it in the context of molecular simulations. Yes, it's essential. People have to realize it. People should see the power, but then it can only scratch the surface. That's, at least that's my own idea, but that's it.
Right, so one more question from Rohit Goswami. It does sometimes feel that there is far too much to cover over time, not just understanding the science, but also the higher level programming. And it's easy to feel a bit overwhelmed, where a project has too many authors, but few people have an overview. Are there any suggestions for these situations? And also, thank you.
No, I think it's a correct statement. I mean, I think, you know, part of the problem of these broad collaborations is that it's lots of people doing pieces, and sometimes I mean, especially, this is especially true of proposal writing, but also to some extent of paper writing, that is basically a lot of pieces just stuck together without necessarily a coherent theme or a coherent question being addressed. So yeah, I mean, I think to develop a real collaboration, especially across a broad set of disciplines, is extremely time consuming. Just within your own discipline, it takes a lot of time to investigate what the other person knows, try to put it together. But if you're now crossing all kinds of fields deep in themselves, yeah, that's a big problem.
Well, maybe, oh, sorry.
Just less haste would be just a huge relief, you know. I mean, I think that, you know, the record shows that Einstein published about 100 papers over his lifetime, maybe not even that many. And it's not unusual for PhD students in some disciplines to publish 50 papers before they graduate. And, you know, this is not just not sustainable. And, or at least it's not sustainable if you're going to do anything really deep, because it's going to take too much time to investigate what you need to know to do something deep. So
yeah, the thing is that this problem with collaboration, so everybody is in favor of collaboration, but if you have a paper where different people bring in different parts, one thing that becomes extremely difficult to detect is fraud. If one author, I mean, I know of examples where actually people, completely respectable scientists, got together, wrote a paper. One person apparently was cheating with some experimental results. How do you know? You trust your collaborators. And still you're being held responsible because you've been collaborating with somebody who published a paper. The paper was fraudulent. There's another thing that I think, and that's maybe a bit more in line with what Tony is saying before, is that among the many pressures there are on sort of starting faculty is the pressure to quickly build up a big group. Now, all the groups at the time when we were students were small. I mean, the typical groups, I mean, the large groups maybe were with like all together, like between 5 and 10 people. Many groups were like a PI and then maybe 2 PhD students. I mean, like 3, 4 people, 5, something like that. Now you see that a successful young scientist, before they know it, they have groups of 20 and may go well beyond that. And the question is, that is being rewarded. So I don't blame them for doing it, but is that really what you want?
I mean, yeah, I mean, that drives me to despair, because I mean, we spend all this time selecting and educating our most creative and intelligent young scientists, and then we put them in a position where they'll never do any actual science themselves ever again. They will review science, they will critique science, they will think of things to try, but they'll never actually go in the lab and make a measurement. They will never run a computer program, let alone write a computer program, and probably never do the actual data analysis. They will look at the results that their students give them, and then if they don't see any obvious flaw, then, well, that's got to be okay, because nobody has the time to do the work that will be necessary to check and make sure that it really is right. So yeah, I think that is a big problem, to me at least. And and that's why I think you land up with so many retractions. I mean, when I was a student, a retraction was essentially unheard of, I think. I'm sure it must have happened, but an erratum now and then. But I mean, now retractions are just normal.
I think it's true, but I think it's, for me at least, it's another one of those areas in which it's difficult to know how much of my thinking has to do with the way I was brought up compared to the way things are today. I mean, but this is probably something to be discussed in front of many glasses of wine in Lausanne or Paris, one street in Paris, because I think this issue of deep versus, depth versus synthesis, vertical versus horizontal. I mean, these are all themes that I think are important and have to do with the way in which we as teachers and senior members of a community also perceive the way in which new people work and deal with things. But I'm not sure that I am making any sense, but I am not always convinced that I am able to fully appreciate the amount of work, intelligence, and depth that goes into the way people that are younger than me run their groups or do their science today. It's I don't know. It's probably maybe one day we should have a roundtable or a Cecam informal discussion about that too, because I find it an interesting.
We should hear from them, because
exactly, and that's the thing, right? Because it's easy, it's difficult. But that said, I mean, proposal fatigue or administration fatigue. These are clearly pathologies that I think we all feel deeply. Yeah. So I mean, with some regret, but I think that we are now at 6:20 here in Lausanne, and it's perhaps time to wrap things up. But before thanking you for this absolutely wonderful afternoon of science, there is something that Nicola has proposed, and that may or may not become, a tradition for this Cecam Marvel Classics series. But I quite enjoy it. We are catching you a bit by surprise, Tony and Dan, so don't worry too much, but it's a rather unconventional question that I feel Nicola should ask you, because it's nice to get to know a bit better before we say goodbye.
Always ready. Thank you, Sarah. And I'll stay on a radio theme, because you see in the 70s, in Italy, Arbor and Boncompagni would sing, no, we are not the BBC. And here instead, we think at ourselves a bit like the BBC. And so we ask the desert island question. That is, if you were stranded on a desert island, that, in these days of pandemics, actually looks quite a reassuring, option. And you could only bring with you, one disc, one piece of music, one book, and one luxury item. What would you bring with you on this island? And I don't know who wants to go first, but you're both very welcome.
I think for the disc, it would have to be some of Leonard Cohen's songs, because I'd be so miserable that he would be the most appropriate companion.
Yeah, I mean, in my case, it would probably be more classical. It would be either Bach or Mozart, but then I would have a hard time to choose which one to bring. but the other things, I mean, with the book, it's almost impossible, because I mean, because in literature, typically I don't read a book twice. And so why would I bring it along to a desert island? I mean, I can't eat it or anything. That's there are certain science books that I would like to read again, because every time you read them again, you see something else. I mean, the ultimate example is Landau and Lifshitz, where every time you read it, you realize that you never understood it before, and then probably the next time you read it, if the opportunity still arises, you find that you didn't understand it the last time. So there are books with many levels, but there's also undoubtedly literature at the same time. So maybe I should just bring Shakespeare.
So I think I would bring Bible, because it's a comprehensive story that's a meaningful one to me, and it's something that I would read over and over. So even though I couldn't eat it, I would think I would probably take it. I know that can be a conventional choice.
And another good example in which the author did not publish that many papers and yet had a fundamental impact on human history.
There's a lot of authors, from what we understand.
And others had not been able to reproduce the experiments. Wasn't it?
Well, thank you very, very much for accepting to play with us today. This was a very nice experience. And I think a confirmation for Nicola, Ignacio, and myself of the fact that this format has quite a few merits. It's very interesting to see how things were born and what impact they've had, and you know, all that comes with the science, right? And we have here Alexandre, who's thanking us for the unorthodox part. Yes, this is the part that I think we are proud of, without forgetting the wonderful and very high quality lectures that we got from Tony and Dan. So thank you for both parts. Just as a reminder, you will find this material stored online, both on the Materials Cloud in the Learn section, on the Cecam YouTube channel, and on the Cecam website, although we are very good at hiding things on the Cecam website. And on that note, I would also like to tell you, if I can find it, just a second here, yes, that the report of Dan and Tony's work in the 1983 Cecam workshop is in fact uploaded on the Cecam website. And this is a PDF that was bravely scanned at Cecam. You can find it. Let me see if I can guide you to it. You go to the Cecam main page. You go to, for example, the menu, other activities, lectures. Here you find today's lecture. You go to lecture. And then if you are patient enough to scroll down just before you find the program, there is a tiny box that will become much bigger in the near future. You click on that and oops, you are on the workshop report.
Very nice.
Wonderful.
Thank you.
Thank you, guys. And thank you very much for spending time with us. Thank you to all those who participated. And Etienne, I think, says it all. Thank you very much. It's very heartwarming for young scientists to feel support from predecessors. So here we are. And looking for, oh, sorry, this was the last Cecam Marvel Classic for this season, but we are already working hard with Ignacio and Nicola to think about new lecturers and fascinating new stories to share with you all in the fall and then in the spring. So looking forward to seeing you all again soon. Okay. Bye. Thank you again.
Bye-bye.
Bye. Bye-bye.
Bye.
Bye.